The Big Bang was the instant when space, time, and everything we know came into existence. But the truth is, we don't really know what happened at that moment. The equations we trust most in physics collapse under the pressure of infinity, leaving us staring at a blank wall in our understanding. What if that beginning was not the start of everything, but just a transition? Could our universe have been born inside another one, like a bubble budding from a greater cosmic sea? Maybe there are countless other universes surrounding us right now, invisible yet real. The Big Bang as we tell it today. The way most of us hear the story of the Big Bang today begins with something deceptively simple. Everything, everywhere, once being squeezed into a state so hot and dense that it defies imagination. There was no space as we know it, no time in any familiar sense, no galaxies, no stars, no atoms, just an almost uniform sea of energy and matter bound together in conditions beyond anything we can hope to recreate. Then, around 13.8 billion years ago, the universe began to expand. Space itself stretching, carrying everything within it outward. From that single blazing beginning, the universe we see today was set in motion. This picture, the standard model of cosmology, is how scientists explain the origins of everything around us. It is a framework that has been tested and confirmed by observation after observation. The simplicity of the idea that the universe began small and grew over time turns out to explain an enormous number of details about how the cosmos looks today. If we were to travel back in time, moving against the flow of expansion, galaxies would draw closer together. Stars and clusters would begin to crowd into a tighter, denser arrangement. Keep going further, and the picture becomes stranger. The matter that now makes up stars, planets, and even ourselves would no longer exist in its current form. Instead, the universe would resemble a hot plasma, where particles are so energetic that atoms cannot even hold themselves together. Push further back still, and even those particles become something more basic, blending into a nearly featureless soup. At some point, just beyond what our physics can currently describe, everything was condensed into that primordial state, the beginning point of the Big Bang model. One of the reasons this story works so well is that it makes clear, testable predictions. For instance, if the universe started hot and dense and then cooled as it expanded, there should still be a faint afterglow from that early heat left behind. In the middle of the 20th century, scientists discovered exactly that, a background of microwaves filling every direction of the sky. This cosmic microwave background, or CMB, is often described as the echo of the Big Bang. It is the universe's earliest visible light, stretched into microwaves as the cosmos expanded. The discovery of this glow cemented the Big Bang model as more than just theory. It became a picture backed by direct evidence. Another feature that fits beautifully into this story is the way galaxies are moving. When astronomer Edwin Hubble studied distant galaxies in the 1920s, he found that almost all of them were receding from us. Not only that, but the farther away a galaxy was, the faster it seemed to be moving. This pattern makes sense if space itself is expanding, carrying galaxies with it like raisins in a rising loaf of bread. The Big Bang model gives a natural explanation for this observation. The universe has been stretching since its earliest moment, so the more distant something is, the longer it has been carried by that expansion. When the universe was only minutes old, it was hot enough for nuclear reactions to occur, fusing protons and neutrons into the lightest elements, mostly hydrogen and helium, with small amounts of lithium. This process, called primordial nucleosynthesis, set the basic chemical makeup of the universe. Billions of years later, when we measure the composition of stars and gas clouds, we find exactly those proportions predicted by the model. It is as though the Big Bang left behind a recipe, and the universe around us has followed it with remarkable precision. Yet, for all its success, the Big Bang is not described as a literal bang. That name is a bit misleading, suggesting an explosion at a single point in space. What scientists actually mean is that space itself was expanding everywhere at once. The universe did not burst into empty surroundings. It was all there was. As space grew, it cooled and structure slowly formed out of the initial uniformity. Over billions of years, gravity gathered matter together, sculpting stars, galaxies, and eventually the grand cosmic web we now observe. Astronomers today can look deep into the sky and see light that has been traveling for billions of years, effectively allowing us to peer back in time. When we look at distant galaxies, we are seeing them as they were when the universe was much younger. These cosmic snapshots confirm that galaxies were smaller, more chaotic, and still coming together in the early days, exactly what the Big Bang story predicts. By tracking how fast the cosmos expands today and comparing it with how things looked in the past, scientists can estimate when it all began. The result, around 13.8 billion years, comes from multiple independent methods. The expansion rate, the CMB, and the ages of the oldest stars all point to roughly the same figure. Few scientific ideas are so widely cross-checked. Of course, this story is still simplified. It leaves out the more complex details, such as the idea of cosmic inflation, an ultra-rapid expansion in the earliest fraction of a second, or the role of dark matter and dark energy in shaping the cosmos. Those are refinements layered onto the framework. But at its heart, the Big Bang model gives us something fundamental, the knowledge that the universe has a history, that it has changed over time, and that by studying it, we can trace those changes all the way back to its fiery birth. It is not a finished story, for new discoveries continue to refine it, but it is a remarkably durable one. For most of what we observe, the Big Bang as we tell it today is the map that makes sense of the terrain. It shows us where we came from, guides us in what we see now, and points us toward the questions that still remain. When time itself began, or did it? In our daily lives, time is simply the sequence of moments, the past leading to the present flowing into the future. We measure it with clocks, with the motion of planets, and with the ticking of atoms. But when you strip everything down to the very first instant, those familiar markers vanish. There were no stars crossing the sky, no particles oscillating, nothing that could act as a cosmic clock. Yet, physics does not stop at intuition. The equations of general relativity, which describe how space and time are connected and how they curve under the influence of matter, can be run backwards in the same way we rewound the expansion of the universe. As you trace the universe back, the equations point to a state where density and temperature climb toward infinity. This is what is called a singularity, a place where the laws of physics break down. At the singularity, time itself seems to collapse. According to this picture, there really is no before the Big Bang. It is not that something happened and then the universe began, but that the very concept of before loses meaning. Many scientists are not satisfied with simply saying time began and leaving it at that. The singularity is less of a real object and more of a signal that our theories are incomplete. It is a boundary, a flashing light warning us that new physics is needed to understand what truly happened at the earliest moments. If we could somehow combine relativity, which governs space and time, with quantum mechanics, which governs particles and forces, perhaps the singularity would resolve into something deeper. That has led to many ideas about what might have happened before the Big Bang. One possibility is that the Big Bang was not the absolute beginning, but a transition. In some theories, our universe could be just one bounce in an endless cycle of expansions and contractions. In such a scenario, time stretches back indefinitely. The cosmos may have collapsed before, reached an extreme density, and then rebounded into expansion again. What we call the Big Bang would simply be the latest bounce, not the start of the clock. This kind of cyclic universe has appeared in different forms over the years, and though it is not the standard view, it shows how the idea of time stretching back further remains possible. Another way of looking at it comes from quantum cosmology. At very small scales, quantum effects can blur the sharp lines of space and time. Instead of a singular point where everything begins, the universe could have emerged smoothly from a prior state governed by quantum rules. Some models suggest that before the Big Bang, time as we know it did not exist, but something else did, a timeless quantum realm that eventually gave rise to our flowing sense of past, present, and future. In this picture, time itself is not eternal, but emerges only once the universe grows large enough for it to have meaning. There are also more radical suggestions. In some theories, the universe might be part of a multiverse. with countless other regions of space and time existing beyond our horizon. The Big Bang would then be a local event, the birth of our particular bubble, while time in the larger multiverse might stretch endlessly in both directions. If true, then the beginning of time for us was not the beginning of everything, but just the start of our patch of reality. Even in the standard Big Bang model, the language of the beginning of time is more subtle than it seems. For everyday purposes, it works well to say the universe began 13.8 billion years ago. But that figure does not point to a sharp edge or a cosmic wall. It points to the limit of what our equations can describe. The human mind struggles with the idea of no beginning. We are used to things having causes, roots, earlier states. To think of time itself as starting abruptly goes against our instinct. That is why so many theories explore alternatives, even if they remain speculative. Some physicists imagine that time is infinite in both directions, with the Big Bang being a kind of pivot or change in its flow. Others propose that time loops back on itself in a grand circle, so that what lies before is, in some sense, also our future. Physics can describe how the universe has evolved from a fraction of a second onward with stunning accuracy. But the very first instant, the border between nothing and something, between no time and time, is still hidden behind the curtain. Was the Big Bang the true beginning, the first tick of the cosmic clock? Or was it just one event in a larger, perhaps eternal, backdrop? The search for answers continues not only through theory, but through observation. By studying the CMB with ever greater detail, scientists hope to find clues about what might have happened before the universe was a few 100,000 years old. Inflation itself raises more questions. Could it go on forever, producing countless universes in its wake? We also turn to the smallest scales, to particle physics and quantum theory, to search for hints. The behavior of particles in high-energy collisions can mimic, in tiny ways, the conditions just after the Big Bang. Though we cannot recreate the moment of creation itself, experiments give us tiny pieces of the puzzle. Perhaps, by unifying our theories of the very large and the very small, we will one day understand whether time began or whether it always was. Until then, we live with the dual image, the singularity problem. If you take a number and divide it by smaller and smaller amounts, the answer grows larger and larger without bound. Divide by zero itself and the answer is undefined, not because something magical happens, but because the operation doesn't make sense. In the same way, when the universe is traced back to a singularity, it may not be describing something real. It may simply be the place where the equations of relativity, so successful on large scales, fail to capture the physics of the very beginning. This is why many scientists believe the Big Bang singularity was not a real state of the universe, but a symptom of using the wrong theory. We can see the same problem appear in black holes. According to relativity, the center of a black hole contains a singularity, a place where matter is crushed to infinite density. Again, most physicists doubt that nature truly contains such infinities. Instead, they believe that our current equations can't capture what is happening in those extreme environments. Just as the singularity inside a black hole tells us we are missing something, the singularity at the Big Bang tells us that the real physics of the beginning is still hidden from us. One way scientists try to move past the singularity is by exploring models where the universe never reaches an infinite density at all. In these models, the universe might have contracted from an earlier state, shrunk to a very small size, and then rebounded into expansion. In this case, the singularity is replaced with a turning point. Another approach is known as the no-boundary proposal. In this view, the early universe did not have a singular starting point. Instead, time and space smoothly curved into existence, much like the surface of the Earth curves without edges. In such a picture, the universe has no sharp beginning. The singularity is avoided not by replacing it with another event, but by changing how we think about the very shape of time. There are also approaches that come from string theory, where the basic building blocks of the universe are not point-like particles, but tiny vibrating strings. In some versions, strings cannot be compressed into infinitely small points, which means the singularity never actually forms. Instead, the extreme density of the early universe is spread out, softened by the nature of these fundamental objects. All these attempts reject the singularity as a final explanation. It is important to note that this is not unusual in science. Placeholders like this have appeared before in history. At one time, physicists spoke of the atom as indivisible, only to later find it contained protons, neutrons, and electrons. At one time, Newton's laws seemed to describe everything, until relativity and quantum mechanics revealed limits to their reach. In each case, the old theory worked incredibly well within a certain domain, but eventually gave way to a more complete picture. The singularity may simply be the next frontier of this process. Echoes before the Bang. Are there traces of a pre-universe? If our Big Bang was the rebound from a previous contraction, it's possible that leftover energy or distortions could have carried over. These could leave their imprint on the CMB. Researchers have looked for unusual circular patterns, alignments, or strange low-temperature regions in the data, wondering if they might be scars from a time before our expansion began. Perhaps the most famous of these searches came from the claim of concentric circles in the background radiation. A group of scientists argued that these circles might be echoes of collisions between gigantic black holes that occurred in a universe before ours. In this picture, each black hole collision would send out ripples of energy, and if our universe grew out of that earlier cosmos, the marks could still be visible as faint rings. The idea sparked excitement, but it also ran into criticism. Other groups of researchers checked the same data and argued that the patterns were just statistical noise, the kind of thing that can appear by chance when dealing with such complex measurements. This is the difficulty with hunting for echoes of a pre-universe. The CMB is incredibly uniform, and the differences across the sky are very small, measured in millionths of a degree. When searching at that level, random variations can mimic signals. Distinguishing a real scar from the noise is like listening for a faint whisper in a crowded room. It requires not only sensitive instruments but also careful statistical analysis. Even then, disagreements arise about what counts as real. Still, the search has not stopped. Some researchers argue that while specific claims like concentric circles may not hold up, the general idea of finding traces of a pre-universe is worth exploring. For instance, some versions of inflation theory predict that if our universe is part of a larger multiverse, collisions with other bubble universes could leave marks. These might appear as odd asymmetries in the CMB, perhaps one side of the sky looking slightly different from the other, or unusual cold spots that don't fit the standard inflation story. One such cold spot has been identified, sparking speculation that it might be the fingerprint of a cosmic collision. Others suggest it could simply be the result of large-scale structures in our universe, like a supervoid. Extracting the faintest possible information from the CMB pushes the limits of observation and theory. Some scientists compare it to archaeology. Most of the ancient record has been eroded or buried, but sometimes, just sometimes, a fragment of pottery remains. The hope is that one day a signal might emerge clearly enough to point to a deeper past. If we were to find evidence of something before the Big Bang, it would change our understanding of what the universe is. The Big Bang would no longer be the absolute beginning, but rather a chapter in a longer story. That story could involve cycles, quantum transitions, or vast multiverses beyond our reach. It would mean that the CMB, already one of the most important discoveries in science, holds even more secrets. For now, the evidence remains inconclusive. Some hints come and go, challenged by new analyses. The cold spot, the circles, the alignments, all remain under debate. Yet each attempt sharpens our tools, improves our instruments, deepens our questions, and forces scientists to confront the limits of their models. Quantum clues, hidden in the first fraction of a second. Quantum mechanics tells us that at the smallest scales, nature does not follow clean, predictable paths. Instead of objects being in one place or another, particles exist in a haze of probabilities. Instead of smooth motion, they flicker, appear, and vanish. These effects are usually invisible in our everyday lives because they cancel out on large scales. But in the early universe, when everything was compressed into a tiny, dense state, These quantum effects may have shaped the entire structure of the cosmos. One of the most important of these effects is known as quantum fluctuation. Even in what we call a vacuum, empty space, tiny disturbances are constantly appearing and disappearing. Particles and fields briefly flicker into existence, borrowing energy for a fleeting moment before fading back out. This is not just speculation. Experiments in particle physics have confirmed that these quantum ripples are real and measurable. In the first fraction of a second, when the universe itself was smaller than an atom, these fluctuations would not have been trivial background noise. They would have been the main actors, laying down the seeds of everything to come. During inflation, tiny quantum ripples in the fabric of space would have been stretched to cosmic sizes. What began as minuscule variations, smaller than atoms, became vast patterns across the sky. Billions of years later, these patterns are still with us. They can be seen in the CMB as tiny differences in temperature. They can also be seen in the way galaxies are distributed across space, forming clusters and filaments that ultimately trace back to those first quantum tremors. In this way, the ghostly flickering of quantum mechanics may be the reason stars, galaxies, and even life exists at all. Uncertainty is another key piece of the story. At the quantum level, there are limits to what can be known. The more precisely you measure the position of a particle, the less precisely you can know its momentum. The more precisely you measure its energy, the less precisely you can know how long it has that energy. This uncertainty is not a flaw in our instruments, but a basic property of nature. In the earliest universe, it meant that nothing could ever be perfectly uniform. There would always be small variations, small departures from balance. These small cracks in uniformity may have been exactly what was needed to allow complexity to form later on. Without uncertainty, the universe might have remained a featureless fog, with no galaxies, no stars, and no planets. In our everyday world, if a ball rolls toward a wall that is too high, it cannot pass through. But in the quantum world, there is a chance, however small, that the ball will appear on the other side as if it had passed straight through the barrier. This tunneling effect happens with particles all the time, and it is a crucial part of how stars shine because it allows nuclear reactions to occur in their cores. Some cosmologists believe that quantum tunneling might also have played a role in the birth of the universe. The universe could have tunneled from a prior state, perhaps from nothingness or from a timeless quantum sea, into the expanding reality we now inhabit. If true, the universe itself might be the result of a quantum leap. There are other, more speculative ways in which quantum mechanics might have played a role. Some theories suggest that time itself may not be continuous, but built out of tiny units, much like matter is built from atoms. If true, then at the earliest scales, time may have behaved very differently than it does today, with quantum effects dictating how one moment gave rise to the next. Others suggest that the universe itself is fundamentally probabilistic, that it might have emerged as one outcome among many possibilities. In this view, the Big Bang was not a single inevitable event, but the result of a quantum choice, with countless other outcomes possible in a vast multiverse. Even if those more adventurous ideas remain uncertain, what is clear is that quantum mechanics cannot be ignored at the beginning. Relativity may describe the broad strokes of the expanding cosmos, but the brushstrokes that seeded all structure were quantum in nature. Without them, the universe we live in would not look the way it does. The challenge is that the quantum world is notoriously difficult to connect with the cosmic one. Quantum mechanics works beautifully in the lab, explaining particles, atoms, and the behavior of light. Relativity works beautifully in the sky, but when we try to use both together, when the universe is both incredibly small and incredibly energetic, they clash. This clash is why the first fraction of a second remains hidden behind uncertainty. Even so, the search continues. Gravitational wave detectors may one day catch ripples from those first moments, vibrations in space-time itself caused by quantum fluctuations amplified during inflation. In high-energy particle experiments, physicists look for hints of new phenomena that could connect the quantum world with the cosmic one. These efforts are a way of peering back into that hidden fraction of a second, trying to glimpse the quantum foundations of the cosmos. The birth of inflation, a band-aid or a window into something deeper. When we look at the universe on its largest scales, in every direction, it has a striking sameness. The CMB has almost exactly the same temperature wherever we look. In the standard Big Bang picture, there hasn't been enough time for far-flung regions of space to communicate with one another. Light and heat can only travel so far, so distant parts of the sky should never have been able to even out to the same temperature. Yet they did. Inflation provides a neat way out of this mystery. If the universe expanded at an extreme rate very early on, then regions that are now incredibly far apart were once close enough to interact and smooth themselves out. On Earth, if you walk in a straight line long enough, you eventually come back to where you started. That's because Earth's surface is curved. But when we look at the universe, the geometry appears almost perfectly straight, with no obvious large-scale bending. The equations of general relativity allow for all sorts of possible shapes, most of them far from flat. Yet for reasons that aren't obvious, the cosmos has ended up right on the razor's edge of flatness. Inflation solves this by stretching out any initial curvature. Just as blowing up a balloon makes a small patch look flatter, inflating the universe makes it appear smooth and straight. It also offers a natural way to understand where the seeds of galaxies came from. It provides a mechanism for how complexity arose from near uniformity. It bridges the gap between the randomness of the quantum world and the grand architecture of the cosmos. But for all its elegance, inflation has its critics. One reason is that it relies on something we've never directly observed, a hypothetical field, often called the inflaton field, which would have driven the expansion. This field is not part of the standard model of particle physics, and no particle tied to it has ever been detected. To some, it feels like inventing a new substance purely to make the equations work out. Others point out that inflation models can be tweaked in so many ways that they can fit almost any observation, making the idea hard to test or disprove. Science relies on falsifiability, the ability to prove an idea wrong if it doesn't match reality. If inflation can always be adjusted to fit the data, does it risk being too flexible to be truly scientific? And yet inflation has passed some very strong tests. The detailed patterns in the CMB match beautifully with what inflation predicts. The discovery of these patterns in the 1990s and early 2000s was a huge boost to the theory. The distribution of galaxies on the largest scales also lines up with the picture inflation paints. These successes keep many scientists confident that, in some form, inflation is pointing us in the right direction. In many versions of the theory, inflation doesn't stop everywhere at once. It may end in certain regions, forming bubbles of space that grow into universes like our own, while continuing in other regions endlessly. This idea is known as eternal inflation. If true, it means our universe is just one bubble in a vast frothing multiverse. Each bubble might have different physical laws, different constants of nature, and perhaps even entirely different kinds of matter and energy. Suddenly, the neat solution to a handful of cosmological puzzles opens the door to a dizzying, almost untestable vision of reality. The story of inflation captures the spirit of modern cosmology. It's a bold attempt to push our understanding back to the first instances of existence, to explain why the universe looks the way it does, and to connect the smallest scales of physics with the largest scales of space. It has brought clarity to problems that once seemed unsolvable. Yet in doing so, it has raised profound new questions. What drove inflation? What stopped it? Could it be tested more directly? And if eternal inflation is true, what does that mean for our place in the cosmos? The hope is that somewhere, in the delicate patterns of radiation, or in the high-energy collisions of particles, a clue will appear. A clue that tells us whether inflation is a temporary scaffold for our understanding, or a genuine window into the deep machinery of the universe. The cyclical cosmos, when one universe hands off to the next. The idea of a cyclical cosmos has deep roots. Long before modern physics, ancient cultures imagined the universe as something eternal, following rhythms and patterns like the seasons of the Earth. These older stories weren't about galaxies or quantum fields, but they carried a similar thought. time is not a straight line with a starting point, but a circle without end. Modern science, with its focus on evidence and equations, has sometimes echoed that old intuition. If a singular beginning is troubling because it implies something from nothing, then cycles offer an alternative. A universe that has always existed, passing through infinite rounds of birth and death. One of the earliest attempts to put this into modern physics was the oscillating universe model. In the 20th century, scientists wondered whether the expansion we see today might one day reverse. If gravity could slow down the galaxies enough, maybe they would stop flying apart and start collapsing back inward. Over immense timescales, the entire cosmos could shrink down, heating up again as everything crowded closer together, until finally it reached a dense state. From that collapse, a new expansion might burst forth, another Big Bang following a big crunch. In this vision, the universe is like a great lung, breathing in and out forever. The oscillating model gives us a neat rhythm, explains why there was a hot, dense state without calling it the first, and even hints that the cosmos might be infinite in time. But there are problems. One major obstacle is the role of entropy, the tendency for disorder to increase over time. If the universe contracts after expanding, it does not return to the same clean state it started from. Instead, each cycle would carry more disorder, more leftover radiation, more black holes, more broken symmetry. Over countless cycles, the universe would become messier and less structured, making it hard to imagine an endless chain of rebirths that always look fresh. Later versions of cyclic models tried to work around this. Some proposed that entropy might be diluted at the start of each new expansion, spread out across an ever larger cosmos, so that the disorder becomes manageable again. Others suggested that the bounce itself might reset the system in some way, erasing traces of the past. These refinements show how scientists often take a simple idea and then wrestle with the details until it either breaks apart or takes on a new form. In more recent decades, the notion of cycles has returned in a new disguise: the ikpyrotic universe and its variations. This model, inspired by string theory, doesn't picture the cosmos as simply expanding and collapsing in 3 dimensions. Instead, it imagines our universe as a kind of 3-dimensional surface, a brane, floating in a higher dimensional space. According to this idea, what we see as a Big Bang may actually be the result of 2 such branes colliding. Each collision produces a hot, dense state, launching expansion, while in the wider framework of higher dimensions, the process could repeat over and over again. In this version of the story, our Big Bang is just one event in a sequence, with no absolute beginning. The appeal of such models lies in how they sidestep the question of singularities. Rather than the universe being squeezed into an impossible point, cycles suggest a smoother handoff from one phase to the next. They also hold out the possibility of explaining features of the cosmos we observe today. For example, why is the universe so uniform across vast distances? Inflation was one proposed solution, but cyclic theories try to explain it through repeated smoothing over long histories. Each cycle, by stretching and resetting conditions, could prepare the ground for the next. Still, while these models can be written down with equations and even made to fit some observations, they face challenges. One is the lack of direct evidence. How could we know for sure that there was a universe before ours? Another is that the predictions sometimes overlap with those of inflationary theory, making it difficult to test which idea is correct. The CMB has been searched for clues of cycles, but so far, nothing definitive has been found. Yet the cyclical view remains attractive to many because it shifts the story of the cosmos from a one-time miracle to a repeating process. It replaces the drama of creation out of nothing with the rhythm of renewal. The bounce hypothesis, replacing the bang with a rebound. Bounce models argue that instead of a singular beginning, what we call the Big Bang might have been the aftershock of a previous universe collapsing in on itself. In this view, the universe emerged out of something old, compressed, and waiting to spring back. This is the heart of the bounce hypothesis, replacing a single sharp beginning with a rebound event. At its simplest, the idea is like a ball dropped on the floor. The ball falls, hits the ground, flattens for an instant, and then bounces back upward. Gravity pulls it down, but energy pushes it back up. In cosmology, a universe collapsing in on itself under the pull of gravity could, in theory, do something similar. It might compress to extreme densities and then, rather than ending in a dead singularity, release that energy outward again in the form of a new expansion. That rebound would look, from our perspective, like a Big Bang. One reason bounce models are attractive is because they try to sidestep the problem of singularities. Instead of shrinking all the way to an impossible point, the universe would reach a minimum size or density and then turn around. This makes the universe less like a line with a start and more like a curve that dips and rises again. Bounce cosmology comes in different flavors. Some are simple, describing a single bounce that gave rise to our cosmos. Others are more elaborate, linking bounces together into sequences, where each universe emerges from the death of the last. But in its cleanest form, the bounce hypothesis doesn't require an endless cycle. It just proposes that what we see as the beginning was really a rebound event after a cosmic collapse. This would mean our universe had a predecessor, even if that predecessor didn't survive in any recognizable way. The mechanics of such a bounce, however, are tricky. Ordinary matter under extreme gravity tends to collapse into singularities, as we see in black holes. If our universe once collapsed, why didn't it end in one big singular state? Some bounce models turn to quantum mechanics for an answer. Quantum effects can sometimes prevent collapse by introducing a kind of quantum pressure. Just as electrons in atoms resist being pushed into the same state, the entire fabric of space might resist being compressed beyond a certain point. Quantum gravity might provide the exact rules. One line of thought comes from loop quantum gravity, a theory that treats space-time itself as woven from tiny, discrete loops. According to this idea, space cannot shrink indefinitely. At some smallest possible scale, compression stops, and instead the geometry of space pushes outward. In loop quantum cosmology, the universe before the bounce contracts reaches this minimum and then expands again. What we call the Big Bang would be the transition point where contraction gave way to expansion. This model has been worked out mathematically, at least in simplified scenarios, and it shows how a bounce could naturally emerge from quantum principles. Another variation looks to exotic forms of matter or energy that might behave differently under extreme compression. For example, certain forms of scalar fields, hypothetical fields that pervade space, can counteract collapse at high densities, acting as a repulsive force that triggers the rebound. This is similar to how inflation models use a field to drive expansion, but here the field works to prevent total collapse. If such a field existed in the earlier universe, it could have orchestrated the bounce. If a bounce did happen, what survives from before? Would anything of a previous universe pass through the transition? Or would the bounce erase all memory? Some theories suggest traces could survive, carried by imprints in the distribution of matter or in patterns of gravitational waves. Others argue the bounce scrambles everything, meaning our cosmos is born with no memory of its parent. Bounce cosmology doesn't solve everything, it only moves the mystery further back, but it removes the sharp edge of a creation event and replaces it with continuity. Bounce models do face challenges, though. One problem is entropy, which again should build up with each cycle, making future universes more and more chaotic. Some scientists argue this makes eternal bounces unlikely unless there is a way to reset entropy after each collapse. A single bounce, however, avoids this problem. In that case, entropy would rise from the bounce forward, but we wouldn't need to explain an endless build-up. Baby universes budding off black holes. Black holes look like a kind of cosmic trap. Nothing can escape its gravity, not even light. To most of us, it seems like the ultimate dead end. Yet some physicists have taken this idea and flipped it on its head. Instead of being an ending, maybe a black hole is a beginning. Maybe when matter falls into one, it doesn't just vanish into nothingness. It could create an entirely new universe on the other side. This idea links two of the most extreme concepts in science: the crushing power of black holes and the birth of whole new realities. To understand where this idea comes from, we need to think about what happens inside a black hole. According to Einstein's relativity, once you cross the event horizon, the invisible boundary around a black hole, there's no turning back. Everything is drawn toward the singularity at the center. That word again, singularity. Perhaps matter falling in gets compressed to such incredible densities that space and time themselves warp and twist into new configurations. Instead of collapsing to nothing, perhaps the matter triggers the birth of a new expanding universe. From the outside, we still see the familiar black hole swallowing stars and gas, but from the inside, the story might be completely different. A fresh cosmos, with its own space, its own time, and perhaps even its own set of physical laws, could be inflating outward. This concept is sometimes described with the language of baby universes. Our universe, on this view, could itself have been born in the depths of a black hole belonging to some older universe. That would mean black holes are not just destructive engines, but cosmic wombs, giving rise to entirely new realms of existence. The scale of this idea is dizzying. When we look at the night sky and see the dark silhouettes of black holes at work, we might actually be witnessing the seeds of universes beyond our own comprehension. There's a certain elegance to this proposal because it ties together two mysteries. On one hand, we have the mystery of what happens inside black holes. On the other, we have the mystery of where our universe came from. The baby universe idea links them. The violent collapse of matter into a black hole might not be an endpoint, but a handoff, where the information and energy are reborn in a new reality. Of course, we can't exactly look inside a black hole to see whether a universe is forming there. By definition, the event horizon hides everything beyond it. That makes the idea almost impossible to test directly. Yet scientists are clever, and they've looked for indirect clues. One way is to study the behavior of black holes in simulations that mix relativity with ideas from quantum physics. These attempts often suggest that the singularity might be smoothed out into something else, something finite. If that's true, then perhaps the wild conditions at the center really could give rise to new space-time regions that branch off from our own. Another approach is to think about whether the structure of our universe hints at such an origin. Some researchers have suggested that the laws of physics we see, the strength of gravity, the charge of the electron, the ratio of forces, might be inherited traits from a parent universe. In this picture, universes born inside black holes might have slightly different laws each time, like children resembling their parents, but not being exact copies. Over countless generations of universes, those with physical constants that allow stars and black holes to form would naturally become more common because only those universes could give birth to further universes. This idea has been called cosmological natural selection. It treats universes almost like living organisms, reproducing and passing on traits. Instead of one universe with one set of laws, reality could be a vast family tree branching out endlessly. Each black hole is like a seed pod, carrying within it the potential for an entirely new cosmos. Our own universe could be just one leaf on an unimaginably large tree of existence, its roots stretching into realms forever beyond our sight. There is no clear observational test that can confirm or refute it. Critics argue that unless a theory makes predictions we can check, it risks being more speculation than science. Others point out that even if universes can bud off from black holes, we might never be able to interact with them. Each baby universe would be sealed off from its parent, expanding in its own space and time, forever separate. To us, it would be as though it never existed. Still, the idea has a way of capturing the imagination. It suggests that creation and destruction are not opposites, but parts of the same process. The collapse of a star into a black hole, which looks like an ending from our perspective, could simultaneously be the most dramatic beginning imaginable elsewhere. Every galaxy, with its millions of black holes, might be a nursery for countless other universes. If our universe was born from a black hole in some older universe, then the Big Bang was just the beginning of our branch of the story. The real tale stretches back through generations of universes, perhaps without end. And if that's the case, then asking what happened before the Big Bang isn't meaningless at all. The answer could be, another universe happened. No telescope can peer into the heart of a black hole. No probe can survive crossing an event horizon. The evidence we need is locked away, perhaps forever. But that doesn't make the idea pointless. Even untestable theories can inspire new ways of thinking, new approaches to physics, and new questions to ask. Sometimes, Daring ideas open paths that later science can follow, even if the first steps are shaky. Brane collisions, the multiverse in higher dimensions. Imagine our universe as a vast, invisible sheet. Everything we know, galaxies, stars, planets, even the laws of physics themselves, exists on this sheet. In the language of string theory, this sheet is called a brane, short for membrane. Now, string theory doesn't stop with one sheet. It allows for many of them, stacked or drifting within a higher dimensional space. If such branes exist, then our universe could be one of countless sheets floating in a grander arena, each carrying its own version of reality. Picture two enormous, invisible canvases moving in higher dimensional space. If they touch, the energy released could be unimaginably powerful. To us, inside one of those branes, the event might look like a Big Bang. What we think of as the beginning of everything might be the aftermath of a cosmic crash between invisible worlds. This picture arises from the mathematics of string theory, which tries to unify all the fundamental forces of nature. But the math only works consistently if extra dimensions exist beyond the three of space and one of time that we experience. In some versions, these extra dimensions allow for the existence of branes of different sizes and shapes. Our universe could be a four-dimensional brane embedded in this higher dimensional space, which string theorists call the bulk. Unlike traditional inflation theory, which introduces a rapid expansion to smooth out the cosmos, this ekpyrotic picture explains the same observations with brane dynamics. If our universe was born this way, what prevents it from happening again? Branes might move, drift, and collide repeatedly over unfathomable stretches of time. This opens the possibility of a cyclical multiverse, where Big Bang-like events happen again and again, not within a single universe, but across a broader dimensional stage. In this view, universes could come and go like waves crashing on a shore, each one leaving behind echoes of its impact. The same mathematics that governs vibrating strings smaller than atoms could also explain why galaxies exist at all. It's as if the smallest and the largest scales of reality are connected by hidden threads woven through higher dimensions we cannot perceive directly. If a brane collision caused our Big Bang, it could have left unusual patterns in the CMB. Some scientists search for such imprints, slight asymmetries or alignments that don't fit with standard inflation. The idea offers a way to think of our universe as part of a larger system, where creation is not a singular miracle, but an ongoing process. It suggests that what we see is only a slice of a grander reality, one that might teem with other branes, other universes, with their own rules of physics. Some could be barren, devoid of matter or light. Others might host stars, galaxies, and even life, though shaped by constants and forces different from ours. We would never know, except through the faintest echoes of past collisions. Instead of asking what happened before the Big Bang, we might ask what governs the movement of branes in higher dimensional space. The Big Bang ceases to be a singular origin and becomes one event in a longer sequence of interactions. Could technology ever pierce the boundaries of our brain? Could signals leak between universes, like whispers through thin walls? For now, these are wild questions without answers. The other side of the Big Bang, a mirror universe. Some theories suggest that when the Big Bang occurred, it might have produced not only our universe, but also a mirror universe, one that is like ours in some ways, but reversed in others. Instead of existing before us, as in bouncing or cyclic models, this mirror cosmos would have been created right alongside us, sharing the same origin point, yet unfolding in a completely different direction. The idea of a mirror universe comes from trying to understand some of the odd puzzles of physics. One of the biggest mysteries is why our universe is made almost entirely of matter, while antimatter, its natural opposite, is so scarce. According to our best theories, the Big Bang should have produced matter and antimatter in equal amounts. But if that had happened, the two would have mostly annihilated each other, leaving behind nothing more than light. Clearly that didn't happen. Somehow matter won, and here we are, living in a universe built out of it. The imbalance has always been troubling for scientists. But what if antimatter didn't simply disappear? What if it went somewhere else? Into a partner universe born at the same moment as ours, carrying away the missing half of the equation. This mirror universe would not be a place we could easily visit, nor one that sits next to us in normal space. Instead, it would be a kind of reflection of our universe across time. One of the ways physicists think about this is by imagining time flowing in opposite directions. In our universe, time moves forward, at least from our perspective, but in the mirror universe, time would run the other way, backward relative to us. To the beings, if any exist, in that mirror cosmos, their sense of time would feel perfectly normal, just as ours does. But from our point of view, it would look reversed, as though they were moving from what we call the future into what we call the past. It's a strange concept, but it emerges naturally in certain mathematical models that describe the universe at its earliest moments. One such idea comes from researchers who study symmetry in physics. Nature seems to love symmetry, patterns that remain unchanged even when you flip, rotate, or reverse things. Our physical laws often work the same whether you run them forward or backward in time, or whether you swap matter with antimatter. But at the scale of the whole universe, these symmetries appear broken. We live in a universe where time has a clear direction. Matter outweighs antimatter, and the arrow of entropy pushes everything toward disorder. A mirror universe offers a way to restore balance. Our universe could be the matter-dominated side, while its twin is the antimatter-dominated side. Our time flows one way and theirs flows the other. Together, the two could complete the symmetry that nature seems to prefer. What would such a mirror universe be like? At first glance, it might look eerily similar to our own. Stars and galaxies could form, light could travel, gravity could sculpt structures. The difference would lie in the composition. Antimatter would dominate. In our universe, if a proton and an antiproton meet, they annihilate into pure energy. In the mirror universe, it would be the opposite. Antiprotons would be normal, and protons would be the rare, destructive counterpart. To beings made of antimatter, their chemistry and physics would still feel perfectly natural. Their atoms, molecules, and even potential forms of life could exist just as comfortably as ours do, though made of the building blocks we consider opposites. If our universes truly split at the moment of the Big Bang, then they may forever remain separated, unable to touch. Yet some physicists wonder if there could be subtle connections, echoes of that twin cosmos visible in the traces of our own. For example, the missing antimatter problem itself might be indirect evidence. Perhaps we don't see it here because it was siphoned away into the mirror. If time flows in the opposite direction in the mirror universe, then in a sense, our two universes are like reflections in a cosmic mirror. The beginning of time for us could also be the beginning of time for them, but with opposite orientations. From our perspective, they move backward, but from theirs, we would appear to move backward instead. Both would be right within their own frames of reference. This dual unfolding could mean that the Big Bang wasn't a single explosion into a void, but rather the splitting of reality into two branches, each one heading away from the same origin, but in reverse directions of time. Some thinkers have asked whether what we call the end of our universe might connect to the beginning of theirs. Imagine the far future, when our cosmos has run its course, stars have burned out, and particles have decayed. Could that ultimate state, that cold and empty stretch, in some way form the starting conditions of the mirror cosmos? In this view, the two universes wouldn't just be born together, they would complete a cycle of reflection, one's end being tied to the other's start. Time itself, usually thought of as a straight arrow, would bend into a strange symmetry across universes. The idea has power because it addresses some of the deepest mysteries: why the Big Bang produced something instead of nothing, why matter dominates antimatter, and why the laws of physics seem to lean toward asymmetry when nature prefers balance. The mirror universe offers an answer that restores harmony, even if it requires us to imagine realities we cannot yet touch. For now, our universe shows no clear scars of its twin, and while we may never meet the inhabitants of that other world, if they exist, the knowledge that such a mirror exists at all would forever change how we see our place in the grand design of reality. Quantum tunneling into existence. Physicist Alexander Vilenkin in the 1980s proposed that the universe could have tunneled into existence from a state of pure nothingness. By nothingness, he didn't mean empty space. Space itself is part of the universe. Instead, he meant a true absence of anything. No time, no space, no matter, no energy, no laws. From that state, the universe could have spontaneously formed thanks to the peculiar rules of quantum physics. To our everyday intuition, this seems impossible. How can something come from nothing? Yet the mathematics of quantum cosmology suggest that it's not only possible, but may even be natural. In this view, the birth of the universe is a quantum event, similar in spirit to the countless smaller quantum events we already know happen every instant at the microscopic level. The Big Bang was not a singular explosion in pre-existing space, but the tunneling of space-time itself into being. Once it formed, inflation would have taken over, blowing up this tiny universe to the vast size we observe today. Without quantum tunneling, inflation might never have had the initial spark to begin. But if universes can tunnel into existence, does this mean there could be countless others? The mathematics seems to allow for it. Each tunneling event could create a universe, sealed off from others, with its own space and time. Our universe might just be one in an infinite foam, each one born from the same process of quantum tunneling. If our universe appeared from nothing, then the laws of physics must have also come into being in that process. They are not eternal truths written in stone, but emergent rules that crystallized when the universe was born. This perspective changes how we think about the ultimate foundation of reality. Instead of laws existing first and the universe obeying them, the laws may arise together with the universe. Quantum tunneling at the scale of universes happens at energies far beyond what we can reach in any laboratory. We cannot create or watch universes appear in controlled conditions. Instead, we can only look for signs in the structure of our universe. Quantum theory requires a framework to operate, so even the idea of tunneling assumes some underlying structure. If so, then perhaps the universe came from some deeper, hidden layer of reality. Just as a pencil balanced perfectly on its tip will eventually fall, nothingness may naturally give way to the birth of something. In that sense, our universe may not be a bizarre exception, but an inevitable result. Could advanced civilizations one day create new universes through quantum tunneling? If the right conditions could be engineered, perhaps an experiment in a far future laboratory might trigger the birth of a new cosmos. In this view, universes might be both natural and artificial, born from both quantum chance and conscious intention. Vacuum decay and the birth of new realities. In physics, the vacuum is the lowest energy state that space itself can hold. But there is a possibility that what we call the vacuum today is not the true bottom of the energy ladder. It could be a false vacuum. If that is the case, then somewhere in the fabric of reality, a shift could occur. A bubble of a lower energy state could suddenly appear, expand at the speed of light, and in doing so, completely rewrite the universe. Imagine the universe as a ball resting in a shallow dip on a hilly landscape. The ball appears to be in a valley, secure in place. But perhaps this valley is not the deepest one. Maybe further along there is a deeper dip. In this analogy, the ball represents the vacuum state of our universe, and the deeper dip represents the true vacuum. If the ball somehow tunneled through the hill separating the two dips, it would fall into the deeper one. For the universe, this would mean an immediate shift in the very laws of physics. Forces, particles, and constants that define our world would all be rewritten. Physicists call this possibility vacuum decay. It is a transition from a false vacuum to a true vacuum, and the consequences are dramatic. Within the bubble of true vacuum, everything would change. The speed of light could be different. Atoms might no longer be stable. Chemistry, as we know it, could fail to exist. Yet within that bubble, conditions could also support a completely different kind of physics, perhaps even a different kind of universe altogether. The mechanism is tied to quantum field theory, the framework that describes particles and forces as excitations in invisible fields spread throughout space. These fields carry energy, and the vacuum represents their lowest possible energy state. But quantum mechanics is never truly still. Under rare conditions, a fluctuation could push a region of space into a more stable state, creating the first seed of a true vacuum. Once formed, the bubble would expand without limit, consuming everything in its path. This scenario might sound like the ultimate cosmic disaster, but from another perspective, it could be a form of cosmic creation. What seems like annihilation from the outside could appear as a Big Bang-like event from the inside. The birth of a new universe would not require a grand external trigger, but could emerge naturally from the instability of the vacuum. Some theories suggest that our universe may already have experienced such transitions in its past. If the vacuum has shifted before, earlier versions of the universe might have been governed by different sets of laws. Each decay would act as a step, moving closer to stability while leaving behind different eras of physics. Instead of beginning from nothing, the universe may have begun when one vacuum gave way to another, unleashing enormous energy as it settled into a new state. This possibility ties closely to the Higgs field, discovered in 2012 with the Higgs boson at the Large Hadron Collider. The Higgs field is crucial because it gives mass to fundamental particles. But measurements of its properties suggest that our current vacuum may not be the absolute minimum of energy. Instead, it may only be metastable, a kind of cosmic balancing act. If so, then the universe is perched precariously, stable enough for life to exist now, but not guaranteed to remain so forever. The slightest disturbance, perhaps even triggered by high-energy events in space, could nudge it toward collapse. However, the timescales involved are staggering. Calculations suggest that if vacuum decay is possible, it may not occur for trillions of years, or perhaps even longer than the current age of the universe raised to unimaginable powers. For all practical purposes, humanity has nothing immediate to fear. Yet the theoretical possibility is enough to provoke awe. It means that the stability of our world depends not on eternal certainty, but on a fragile balance in the quantum fabric of reality. If a bubble of true vacuum did appear, its expansion would be unstoppable. No warning would reach us, because the bubble's edge would move at the speed of light. One moment, the universe would appear as it always has. The next, the laws of physics would shift completely. Yet, within the bubble, new possibilities could unfold. Some scientists wonder if the expansion could resemble inflation. In that case, the bubble would grow into a self-contained cosmos with its own space. From the perspective of future beings within that bubble, it would appear to have begun with a Big Bang. The idea also connects to multiverse theories. If our universe is just one vacuum state among many, then there could be countless others existing already. Each region of the cosmic landscape might host a vacuum with different properties, separated by vast distances or barriers that cannot be crossed. From this perspective, the birth of universes through vacuum decay is not rare, but natural. It could be happening elsewhere, right now, in corners of reality beyond our reach. At the same time, some physicists caution against taking the idea too literally. The mathematics of vacuum decay is elegant, but it depends heavily on assumptions that may not reflect the full truth of the universe. Our knowledge of quantum fields is incomplete, and it may turn out that the vacuum is far more stable than current models suggest. Or perhaps the vacuum decay process creates outcomes stranger than any prediction. Is the universe safe, or is it fragile? Are we living in a reality that is permanent, or are we part of a temporary phase destined to give way to something new? And if the latter is true, then perhaps our universe is part of a chain of creations, each born from the collapse of the last. This thought is both unsettling and strangely comforting. It means that endings are not absolute. Even if our universe were to fall into a new vacuum, the process would not be one of erasure, but of transformation. The same quantum rules that allow for the possibility of destruction also open the door to creation. Mathematical universes. Does reality follow every equation? What if mathematics was not just a language we use to describe the world, but the very foundation of existence itself? What if every consistent mathematical pattern, every equation that holds together logically, could exist as its own universe? Our universe, then, would not be unique. It would be one instance out of an endless library of mathematical realities, each with its own rules, its own shapes, and its own forms of existence. This idea is sometimes called the mathematical universe hypothesis. It is most closely associated with the physicist Max Tegmark, who argued that reality might be nothing more than mathematics expressed on a grand scale. The theory begins with a simple observation. So far, everything we know about the universe can be described in mathematical terms. From the path of a falling apple to the orbit of planets, from the bending of light to the behavior of subatomic particles, equations capture the patterns that unfold. The strange part is not that math describes these things, but that it does so with such precision that the world seems inseparable from the mathematics itself. If math works so well here, perhaps the reason is because the universe is math at its core. Now imagine extending that thought. If our universe corresponds to one set of equations, what about all the other equations that are internally consistent? Why should only this particular set exist? If logic allows for other possibilities, then perhaps those possibilities are not just abstractions. Perhaps they are real universes, existing independently, running on the rules of their own mathematics. Instead of other universes being born from quantum fluctuations or cosmic inflation, they would exist because mathematics itself generates them. It is a dizzying suggestion. Some of these mathematical universes would resemble ours. Others would be utterly alien. For example, imagine a universe where geometry works differently, where triangles don't add up to 180 degrees, or where time is not a line, but loops back in intricate cycles. There could be universes with no time at all, where the concept of change does not exist and everything simply is. Or universes where the number of spatial dimensions is so large that movement, form, and structure would be incomprehensible to us. Mathematicians routinely deal with abstract structures that follow consistent rules, even if they don't apply to our physical universe. A mathematician might study a world of four-dimensional spheres or equations that describe objects beyond visualization. If the mathematical universe hypothesis is true, those abstract forms are not just mental exercises. They could be as real as our own world, existing somewhere beyond our perception. In our everyday experience, existence means something physical, something that can be touched, seen, or measured. Yet in the mathematical universe picture, existence simply means being logically consistent. If an equation can hold together without contradiction, that alone could be enough for it to count as a universe. In this way, the boundary between thought and reality dissolves. If every mathematical possibility exists, then we should not be surprised to find ourselves in one of the few universes where conditions allow life. Our universe is special, it is one of many, and life can only appear in the ones that permit it. Not everyone accepts this vision. Critics argue that just because a structure is consistent on paper does not mean it actually exists. After all, we can imagine a game of chess being played endlessly, with all possible moves explored. But that does not mean all those games are happening in reality. They are potential, not actual. By the same logic, mathematical structures could be possibilities, not universes. Others argue that the mathematical universe idea might not count as science. Any observation we make would simply be explained as part of the universe we happen to inhabit. In this way, the theory risks becoming unfalsifiable. Despite these concerns, the idea continues to attract attention because it connects with something undeniable, the deep and mysterious link between mathematics and the natural world. Time and again, discoveries in physics have revealed patterns that mathematicians had worked out long before. The equations of general relativity, the symmetries of quantum mechanics, the geometry of curved space, all were hidden in mathematics before they were seen in nature. It often seems as if the universe is following a script written in mathematical language. If mathematics defines existence, then perhaps consciousness itself is part of a mathematical pattern. In this view, minds are not tied only to biological brains. Any system that follows the right rules could give rise to awareness. That would mean that somewhere in some mathematical universe, very different forms of intelligence could exist, not made of matter at all, but emerging from abstract relations. It may be that our universe's connection with mathematics is not because it is math, but because math is the best tool our minds have for describing patterns. In this interpretation, mathematics is like a map. It is not the territory itself, but it captures enough of the features that we can navigate the landscape. Just as maps can be drawn in different ways depending on what you want to highlight, so too can different mathematical models describe the same reality. If this is the case, then the universe is not identical to mathematics, but mathematics remains the most powerful lens we have for making sense of it. The question then becomes whether reality is discovered or invented. Do we uncover mathematical truths that were always there, waiting to be found, or do we create them as a product of human thought? If mathematical structures exist independently of us, then perhaps universes exist independently as well. But if math is partly a human invention, then perhaps the idea of mathematical universes tells us more about our imagination than about reality itself. Entropy reversal. Could time run backward across the bang? Time is something we take for granted. It flows in one direction. We wake up, grow older, remember the past, but not the future, and watch order turn slowly into disorder. This arrow of time is tied deeply to the concept of entropy, the natural tendency for systems to move from organized states into more chaotic ones. But what if this arrow is not universal? What if time does not always point the same way everywhere? And what if the Big Bang itself marked not just the beginning of our time, but also the beginning of another, running in the opposite direction? Some physicists have suggested exactly this, that a mirror universe was born alongside ours, identical in its physical laws but flowing through time in reverse. The idea comes from looking at one of the deepest puzzles in modern science: why the universe began in such an extraordinarily low entropy state. Entropy, in simple terms, is a measure of disorder. If you smash a glass on the floor, the pieces scatter randomly and the entropy increases. The reverse, the scattered pieces jumping together into a whole glass, is so improbable that it is practically impossible. Yet the Big Bang began with an almost perfectly ordered arrangement of matter and energy, something so precise that it seems to beg for an explanation. Why would the universe start so neatly when everything we observe tends toward messiness? One way to answer this is to suggest that the Big Bang was not a one-sided event, but a two-sided one. From the singularity, or the earliest possible state of existence, two universes could have emerged. One expanding forward in time, which is the universe we live in, and one expanding in the opposite direction. To the inhabitants of that other universe, time would appear to flow normally, just as it does for us. Their physics, their chemistry, their daily experience of cause and effect would all feel consistent. But from our perspective, their arrow of time would be reversed. This raises the question, what would such a time-reversed universe look like? Would its stars form in the same way? Would life evolve? Or would it be a place where everything seems to run backward, like watching a movie in reverse? The truth is stranger. For those inside that universe, nothing would appear backward. An egg cracking, a person speaking, a galaxy forming. Each would happen as naturally as it does here. It is only from our frame of reference that their entire timeline would appear reversed, starting at what we would call their end, and moving toward what we would call their beginning. To picture it, imagine standing on the edge of the Big Bang. From that central point, our universe races outward with time flowing forward. On the other side, another universe races outward with time flowing backward. Neither side can cross into the other, but both share the same root in the initial explosion. The Big Bang becomes not just the start of everything, but the meeting point of two opposite temporal streams. One of the strongest motivations for this idea is symmetry. Physics often strives for balance, for equations that work the same way no matter which direction you look at them. Many of the fundamental laws of nature are time reversible. If you watch two particles collide and then reverse the tape, the reversed motion still obeys the laws of physics. At the deepest level, nature does not seem to prefer one direction of time over the other. So why does the universe we live in have such a clear arrow of time? Perhaps it doesn't, not in the bigger picture. Perhaps the total cosmos is perfectly balanced. One universe flows forward, the other flows backward, and together they form a complete symmetry. This concept also helps soften the question of fine-tuning. If entropy is always increasing, then the early universe must have been incredibly low in entropy for there to be room for it to grow. That state looks unlikely and special. But if the Big Bang is the middle rather than the beginning, then both sides naturally begin in low entropy and move toward higher entropy in opposite directions. In other words, the symmetry explains the mystery. The Big Bang stops being an unlikely exception and instead becomes a natural dividing line between two arrows of time. Of course, this remains highly speculative. Testing such an idea is incredibly difficult, since we are locked inside our own arrow of time. From our perspective, the other universe is unreachable. We cannot send signals across the divide, nor can we receive any. The Big Bang itself acts like an event horizon, a boundary beyond which no information can pass. Even if the mirror universe exists, it may be forever hidden from us. But some physicists wonder if there might be indirect traces. Perhaps the conditions at the Big Bang were shaped not only by our side, but also by the need to balance both sides. Tiny details in the distribution of matter, or the behavior of cosmic radiation, might hold hints of this symmetry. In practice, however, no clear evidence has been found. The theory lives mostly in the realm of mathematical possibility and philosophical reflection. Still, the thought of a universe where time runs the other way is hard to shake. What would beings in that world think of us? Would they see us as reversed, or would we be entirely outside their perception? To them, their universe is as ordinary and forward-moving as ours is to us. The strange reversal only appears when we compare both sides. It highlights how much our sense of reality depends on perspective, and how what feels absolute to us, like the flow of time, might not be absolute at all. There is also a deeper question. What does it mean for time to reverse? We imagine rewinding a tape, but in physics, time is not just a sequence of events. It is part of the fabric of the universe, woven into space itself. If another universe truly flows in the opposite direction, it challenges our most basic assumptions about beginnings, endings, and causality. Perhaps to see the full picture, we must accept that the cosmos is larger and stranger than any single arrow of time can describe. In this way, the idea of a time-reversed universe is less about running events backward and more about restoring balance. It suggests that our universe is not a lonely outlier, but one half of a greater whole, a cosmic reflection born in the same fiery moment. Whether or not we can ever prove its existence, the idea forces us to rethink what the Big Bang really was. Not just the dawn of our reality, but the meeting point of two universes, each unfolding its own story in its own direction through time. Strange matter clumps. Are they relics from a universe before ours? Some theories hint that traces of what came before the Big Bang may still linger, hidden in rare and exotic forms of matter that could have survived across cosmic cycles. One of the most intriguing candidates for such relics is something called strange matter. Strange matter is linked to the world of quarks, the elementary particles that make up protons and neutrons. In ordinary matter, quarks come in two main varieties, up and down. Combine them in different ways, and you get the familiar building blocks of atoms. But in high-energy environments, such as the interior of neutron stars, other types of quarks, strange quarks, may come into play. When strange quarks mix with up and down quarks, they form a special state of matter that could be more stable than anything we encounter in everyday life. Some physicists speculate that once formed, strange matter might never decay, persisting even when the rest of the universe changes around it. What if some of it predates the Big Bang? If strange matter is as stable as some theories predict, it could have survived a transition from one cosmic cycle to the next. That would make it a messenger from a time before our own cosmic clock began. A fragment of a universe older than the one we know. Physicists sometimes imagine strange matter forming compact clumps or nuggets. These would be incredibly dense, far more compact than any ordinary rock or planet, but not quite as extreme as black holes. If they exist, they could be roaming through space largely unnoticed, perhaps hidden among dark matter or drifting in interstellar regions. Detecting one would be difficult, but not impossible. The passage of a strange matter nugget through a planet's crust, for instance, might leave unusual traces in geological layers, or its gravitational pull might produce subtle signals in astronomical observations. Experiments on Earth have searched for hints of strange matter. particle accelerators smash protons and heavy ions together at high energies, sometimes producing fleeting states of quark matter. In rare conditions, these collisions might briefly generate small samples of strange matter. Most of the time, such exotic states decay almost instantly. But if strange matter is truly stable, even a tiny fragment could in principle survive. So far, no convincing evidence has been found, but the possibility continues to inspire research. If such relics were found, the implications would be extraordinary. For one, it would mean the Big Bang was not the absolute beginning. It would also mean the laws of physics permit continuity across cosmic boundaries, something that challenges the idea of a clean separation between universes. Strange matter would act like a fossil, not of biological life, but of entire universes. The search for strange matter is not limited to theory. Some researchers have speculated that strange matter clumps could explain certain unexplained astrophysical signals. For example, sudden bursts of energy or unusual cosmic ray events might result from collisions involving these relics. Others have suggested they could account for part of dark matter. If strange matter is both stable and abundant, it could be lurking all around us, influencing the cosmos. But detecting something that is rare, compact, and possibly invisible except through gravity is no easy task. Strange matter nuggets would not shine like stars or reflect light like planets. Their small size and huge density mean they could pass through ordinary matter with little interaction, leaving behind few observable traces. Only indirect methods, like gravitational lensing or precise measurements of astrophysical signals, might reveal their presence. Even then, distinguishing strange matter from other exotic possibilities would require careful study. Strange matter has never been observed in nature, only hypothesized based on extensions of known physics. The stability of strange quark matter is still debated, and some calculations suggest it might not be as long-lived as early theories predicted. If it cannot survive for billions of years, then the dream of it carrying messages from before the Big Bang collapses. In that case, strange matter would remain a fascinating theoretical construct, but not a bridge to earlier universes. Still, the idea resonates because most discussions of universes before ours are philosophical, beyond the scope of measurement. Strange matter, in contrast, is something we could, at least in principle, touch, study, and confirm. It transforms the abstract problem of cosmic origins into something that might leave a mark in a detector. Throughout history, traces of the past have often been found in unexpected places. Fossils in rocks, radiation left over from the early universe, ancient ice cores that record climate shifts. Strange matter, if real, would be the deepest trace of all. Cosmic seed banks. Could universes plant the next generation? Just as seeds contain DNA that determines the traits of the plant that grows, the constants and physical laws of a universe could be seen as its genetic code. When a new universe is born, perhaps inside the heart of a black hole, or through some other unknown mechanism, it might not start from scratch. Instead, it could carry imprints of the parent universe's rules, ensuring continuity. The constants might not be identical, but close enough to resemble family traits. Imagine that somewhere beyond our reach, universes branch off endlessly. Each branch begins with an initial imprint, perhaps a slight variation in the mass of fundamental particles or the density of vacuum energy. Most branches collapse quickly, never forming complex structures. A few persist long enough to produce stars and galaxies. Fewer still create the stable chemistry that allows life. From this perspective, the fact that our universe exists as it does is not because it was uniquely favored, but because only universes with these traits survive long enough to be noticed. The seed bank would ensure that traits favorable to persistence, like balance forces and long lifespans, are more likely to appear again and again. Normally, when scientists look at the constants of nature, they wonder if there is a deeper equation that forces them to take the values we see. For example, why is the speed of light what it is, or why is the electron so much lighter than the proton? In a seed bank view, these values may be the result of inheritance and variation, with no single necessity behind them. Just as the height of trees in a forest can be traced to a mix of genetic traits and environmental pressures, The constants of our universe might be outcomes of a larger evolutionary process we cannot fully observe. On Earth, seed banks are collections of genetic material stored to ensure survival against catastrophe. In the cosmos, a seed bank would be a metaphor for how universes protect the possibility of their kind continuing. If one universe fails, its constants leading to instability or collapse, others take its place, carrying similar traits into the future. This creates resilience, a kind of cosmic insurance policy against nothingness. If universes evolve, then perhaps we could one day look for fingerprints of this process in the structure of our cosmos. For instance, is the distribution of black holes unusually optimized? Do the constants seem balanced in ways that hint at selection pressure? These questions are difficult to answer, but they give scientists a framework for exploring the possibility. Some thinkers even suggest that if universes inherit laws, then in some sense they may carry memory. Not memory in the human sense, but a continuity of structure and possibility. The stars above us might reflect choices made not by a single act of creation, but by a lineage of countless universes that shaped the rules to favor such outcomes. This would mean that our very ability to ask these questions is a product of cosmic heredity, the flowering of seeds planted long before our universe began. Seeds are small, fragile things, but they hold the potential for entire worlds. If reality truly works in this way, then every black hole, every collapse, and every new burst of space-time is another seed scattered into the void, waiting to grow. The cosmos, then, would not just be an endless expanse of stars, but a living system of generations, carrying forward the possibility of existence itself. Can physics handle infinity? Infinity is one of those concepts that feels natural to us in imagination, but becomes almost impossible to tame when placed under the lens of physics. Children can easily grasp the idea of numbers going on forever, or the possibility of endless space. Yet when scientists actually try to use infinity in equations or models of the universe, it often leads to strange contradictions or dead ends. The multiverse, with its suggestion of countless, possibly infinite universes, forces us to confront these problems head-on. If there truly are infinite universes, how do we make sense of that? Can we even do science in a framework where there's no limit, no final number, no end? To understand the difficulty, it helps to consider how infinity shows up in mathematics. Mathematicians treat infinity not as a number, but as an idea, a concept that describes something unbounded. You can add 1 to the largest number you can imagine and still not reach infinity. In math, this is fine. There are entire branches of mathematics that carefully define how infinities behave, with different sizes of infinity and rules for how they can be compared. But when physics borrows infinity from math, it tends to break things. For example, if a theory predicts that some measurable quantity, like the density of energy or the curvature of space, becomes infinite, instead of describing reality, the equations are telling us something is wrong here. Now imagine what happens when the idea of infinity is applied to the entire universe, or to the multiverse. If there are infinite universes and each one may contain infinite space, then how can physics ever compare, count, or measure anything meaningfully? This is known as the measure problem in cosmology. Imagine you want to calculate the odds of some feature of our universe, for example, the value of the cosmological constant, the mysterious energy that drives cosmic acceleration. If there are only a handful of universes, this is straightforward. You could, in principle, say one universe has this property, another has that, and then assign probabilities. But if there are infinite universes, each with its own set of constants, how do you even begin to talk about probability? If everything happens infinitely many times, then anything that is possible becomes inevitable. The distinction between rare and common events collapses. This leads to paradoxes. One well-known example is the so-called Boltzmann-Brane problem. In an infinite universe, or infinite multiverse, random fluctuations could, in theory, spontaneously assemble into self-aware observers. These branes would pop into existence, complete with false memories and perceptions. If the multiverse is truly infinite, then there would be far more of these freak observers than beings like us, who arose through billions of years of cosmic evolution. That would mean the most likely observer in the multiverse is not a person living in a vast, stable cosmos, but a lonely consciousness that blinked into existence from chaos. This conclusion feels absurd, but it shows how infinity makes probability meaningless in ways that challenge both science and intuition. Physicists have tried to tame infinity with different tools. Some suggest we need to cut infinity down to size by imposing boundaries, like only considering a finite region of the multiverse, or weighting certain universes differently. Others argue that infinity may not exist at all in nature, it's just a mathematical illusion. For instance, quantum gravity might reveal that space and time are granular, with the smallest possible unit. In that case, infinities would never actually appear, because nothing can shrink or expand beyond those fundamental limits. But infinity has a stubborn way of creeping back in. Even if space and time are quantized, there might still be infinitely many quanta. Even if universes are finite in size, there might be infinitely many of them. Each time physicists try to eliminate infinity, it finds another path into the conversation. This persistence may be because infinity is a genuine feature of reality, not just a flaw in our equations. If so, then science will need to develop new ways of handling it without falling into paradox. One path forward may be to think of infinity not as something to calculate directly, but as a backdrop against which relative comparisons can still be made. For instance, if there are infinitely many universes with different laws, perhaps we cannot measure how many of each kind exist. But we might still be able to identify patterns, like whether certain laws naturally arise more often due to the way universes form. Instead of trying to count infinities, we could search for the biases in the system that tip the scales. This is similar to rolling dice an infinite number of times. You don't count all the rolls, but you can still describe the distribution of outcomes. Perhaps our confusion about infinity comes from a limited perspective. Maybe we expect the universe to conform to human notions of probability and counting, but reality doesn't work that way. Just as relativity forced us to abandon the idea of absolute space and time, or quantum mechanics forced us to give up certainty, the multiverse might force us to rethink what probability means in an infinite setting. Instead of seeing infinity as a failure, it could be the doorway to a deeper understanding of how reality organizes itself. The Greeks debated whether infinity was potential or actual, whether it was just an endless process of adding one more, or whether infinity itself could exist as a real thing. Today, physicists face the same debate, only with universes instead of numbers. Does infinity exist out there in nature, or is it only in our minds? How do we test theories that invoke the infinite? How do we make predictions in a cosmos with no bounds? These challenges show why the multiverse, while captivating, pushes science into its most difficult territory. Are universes like simulations within larger systems? If the universe is governed by laws that operate like rules, and if its state changes moment by moment in response to those rules, then it begins to resemble a vast system of computation. From this perspective, the universe is not simply physical, it could be informational, like a running program. And once that idea takes hold, another question naturally follows. Could our universe be a simulation? And if so, who or what is running it? Some researchers point out that if civilizations survive long enough and their technology becomes unimaginably advanced, they might develop the ability to create artificial realities indistinguishable from real ones. If countless simulations are run, then statistically there could be far more simulated universes than natural ones. In that case, our own existence might be more likely to be inside a simulation than outside one. It's a strange twist of reasoning, but it has been discussed by philosophers and physicists alike. This differs from black hole or parent universe ideas because it doesn't require a physical process of birth at all. In the black hole picture, a collapsing star creates a pocket of space that grows into a new cosmos. In the parent-child lineage view, larger universes might generate smaller ones as part of an ongoing process. But the simulation idea skips the physics altogether. Instead, it replaces it with computation. The birth of a universe would be the pressing of a button, the starting of a program, or even the operation of natural information processing that we do not understand. In that sense, universes could be nested like files within folders, each one running inside another. Ours might itself be a simulation running inside another reality, which could itself be simulated in something beyond that. The chain could be infinite, or it could stop at some ultimate level. To picture this, one might imagine how video games work. Within the game world, there are landscapes, skies, and characters. The characters act as though their environment is real. Yet, from our perspective, we know it is all numbers, stored in memory and processed by chips. If those characters could somehow become self-aware, they might ask questions similar to ours. What is our universe made of? Why do these rules govern us and not others? Could there be a higher level of reality outside this one? From their perspective, the pixels, code, and logic would be invisible, just as deeper layers of existence are hidden from us. And if their game world included simulated computers inside of it, those might run smaller programs, creating yet more layers. The analogy is imperfect, but serves as a way to imagine the hierarchy. Some have wondered if there might be detectable glitches or patterns that betray a simulated universe. For instance, if the universe had to be computed, perhaps it would not simulate everything down to the finest detail. Maybe it would cut corners, only filling in details when observed, similar to how graphics in a video game only render what is in view. Quantum mechanics already presents puzzles that seem oddly aligned with this. Particles behaving one way when unobserved and another when measured. While mainstream physics doesn't treat this as evidence of simulation, the comparison is tempting. Others have suggested that physical constants could be the settings of the simulation, chosen arbitrarily by whoever or whatever runs it. Yet to ground the idea, one has to step back and think about what computation means. A program is not magic. It is a set of instructions that evolve according to logical rules. In that sense, the laws of physics we already know could themselves be seen as a kind of code. Atoms follow rules. Energy follows rules. Space and time evolve in consistent ways. The whole structure of reality looks, in some sense, computable. This doesn't mean we are simulated in a literal sense, but it raises the possibility that information is just as fundamental as matter and energy. In fact, some physicists argue that information might be the most basic ingredient of the universe, with everything else emerging from it. If that is true, then perhaps universes aren't simulated by external beings, but are naturally arising computations, part of the way reality functions at its deepest level. If we allow for the idea that simulations can exist, we also have to consider the implications. If civilizations can create simulated universes, then what stops those universes from creating their own? Perhaps our own universe, if advanced enough, will one day produce artificial realities filled with conscious beings, who in turn create realities of their own. This would result in a vast pyramid of nested universes, each branching from another. The higher you go up the chain, the fewer real universes there might be. At the base, perhaps only one or a handful of original universes exist, while billions upon billions of simulations cascade downward. But here lies a philosophical puzzle. If simulated beings can still think, feel, and experience their worlds as real, then what difference does it make if their universe is simulated? For those inside, reality is reality. Their universe may not be base reality, but it is still their only reality. The distinction between natural and artificial begins to blur. Some thinkers have even suggested that being in a simulation might not lessen the value of existence at all. The laws we observe, whether chosen by coders or emerging naturally, still shape our experiences. Life, meaning, and exploration would still matter within such a framework. Critics of the simulation idea point out that it may not be testable, which puts it outside the usual boundaries of science. To prove we are in a simulation would require evidence from outside the system, but by definition, everything we measure is inside. This makes it more like a philosophical lens than a scientific hypothesis. Yet, as with many ideas in cosmology, the value may not lie in immediate proof, but in stretching our imagination about what is possible. It forces us to think about reality in new ways, comparing it not just to physical processes, but to systems of information and logic. Some wonder if we are thinking too narrowly by comparing the universe to human-made computers. Perhaps reality processes information in ways far beyond anything we know, not as bits of 0 and 1, but through deeper principles of order and pattern. If that is the case, then even the word simulation might be misleading. Our universe might not be fake in any sense, but still exist as one informational layer within a larger system. In that picture, computation is not something added onto physics, but is physics itself, written at its deepest level. Could advanced civilizations manufacture universes? If humans once wondered whether gods or deities created the cosmos, this modern speculation wonders whether intelligence, of any kind, could eventually become so powerful that it can set the laws of physics in motion, sparking new realities entirely. At the core of this idea is the recognition that our universe is governed by rules. If these rules are not arbitrary, but instead are parameters that could in principle be adjusted, then one can imagine a system in which those rules could be set differently. The concept of universe creation begins here. Could it be possible to arrange matter and energy in such a way that a new cosmos blossoms outward, following its own rules, completely cut off from the one that generated it? The seed of a universe, in this view, would not necessarily require divine action, but might instead emerge through deliberate design. In some theories, every black hole might be a natural universe generator, endlessly producing offspring universes beyond the reach of their parents. The leap made by more speculative thinkers is this: if nature can do it, could intelligence learn how to replicate or even improve the process? Could beings at a far more advanced stage of development than us build their own black hole-like systems to deliberately launch new universes? Life and intelligence might not simply be byproducts of cosmic rules, but could become agents in shaping the ongoing branching of reality. Humanity might one day step into the role of gardener in a multiverse full of growing seeds. But what would it actually mean to manufacture a universe? One possibility is that it would involve extreme manipulation of energy. To trigger a Big Bang-like event, one would need to compress and destabilize energy at scales we can hardly imagine. This is not simply a matter of harnessing the power of stars. It would require control at the level of space-time itself. Some physics suggests that high-energy particle collisions, far beyond what our current accelerators can achieve, might create tiny black holes. Normally, these would evaporate almost instantly through Hawking radiation, but in some models, they could pinch off into their own expanding universe, disconnected from ours. If this is possible, then in principle, an advanced civilization could construct the conditions necessary to push such an event deliberately. It is possible that our universe itself was created by some prior intelligence, experimenting or deliberately designing the conditions for a cosmos that could allow complexity to emerge. This would not necessarily mean that our universe was created for us. It could have been an experiment with no thought of what it would produce, or perhaps even a failed attempt that just happened to give rise to a reality filled with galaxies, stars, and eventually life. To us, it looks like the totality of existence. To its creators, it might have been one test among many. Every civilization faces existential threats. Even if a society achieves mastery over its own star system, it may eventually face the slow running down of entropy. Creating new universes could be a way to extend continuity. On the other hand, the motivation might be more scientific or artistic. If universes can be created by intelligence, then perhaps the process is recursive. Our universe could be the creation of another, which itself might have been the creation of yet another, stretching back into a chain of realities, each linked by acts of universe making. In such a scenario, natural origin stories and artificial creation become blurred. Of course, there are profound technical and philosophical barriers to all of this. First, we have no evidence that universes can actually be created. Theoretical models remain speculative, often balancing on the edge of what our mathematics can handle. Even the concept of a black hole giving birth to a new cosmos is not widely accepted. Second, even if it were possible, the energy scales required are beyond anything we can realistically imagine controlling. We are still a species that struggles to harness fusion on Earth. The idea that we could one day sculpt space-time into a new Big Bang belongs to a realm of thought so far beyond our reach that it may never leave the pages of imagination. Yet considering such ideas forces us to think more deeply about the relationship between intelligence and the cosmos. If life evolves naturally within universes, and if intelligence is one of the outcomes of that life, then perhaps intelligence is not an accident, but part of the broader machinery of cosmic evolution. Intelligence might be one of the mechanisms by which universes reproduce themselves, ensuring that existence is not a static one-off event but an ongoing cycle of creation and transformation. If civilizations can build universes, and if our own universe looks strangely well suited for life and complexity, how certain can we be that we are not already living inside the creation of someone else? Why create a universe? It is one thing to imagine that universes can exist beyond our own. It is another to take the thought further and ask whether they could be created deliberately, not by blind natural forces, but by choice. If that is possible, even in theory, why would someone or something do it? Why would an advanced civilization decide to make an entire universe, rather than simply live within the one they already have? One of the simplest reasons is survival. Even the most advanced civilizations would eventually have to face the fact that their universe has a time limit. Stars die, galaxies drift apart, black holes evaporate, and one day the cosmos itself may end in heat death or collapse. If you knew that the place you lived in was temporary, what would you do? On Earth, we build shelters, spread to new lands, and develop technologies to adapt to changing environments. A far greater version of that same instinct could play out on the universal scale. If your universe is doomed, the ultimate form of migration might be to create a new one. In this way, universe creation would not be a luxury or an experiment, but a desperate act of survival. A civilization could pour its knowledge and resources into making a fresh cosmic arena where life could continue when this one fades away. Survival, however, is only one motive. There is also the drive to expand. Human history shows that civilizations rarely remain content with what they have. They explore, they colonize, and they build beyond necessity. If life behaves in similar ways elsewhere in the cosmos, then it might reach a point where even entire galaxies are not enough. Once the physical limits of their home universe are reached, the next frontier would not be another planet or star system, but another universe entirely. Creating one would be the ultimate act of exploration, a way of stepping beyond the boundaries imposed by nature itself. In this sense, universe making could be viewed not only as survival, but as ambition, the desire to go where nothing else has gone. Beyond survival and expansion lies another motive: legacy. Civilizations do not simply want to exist, they want to matter. Humans have written stories, built monuments, and launched artifacts into space, not because these things help us survive, but because they carry our memory forward. Imagine a civilization capable of creating a universe. Such an act would be the greatest monument of all, a structure that does not crumble with time because it contains time itself. A species might do this not for themselves, but for what comes after. They may hope that intelligent beings inside the new universe will one day discover their origins, or perhaps even see clues written into the fabric of reality. To leave behind a universe is to leave behind a legacy that no disaster could erase. Another idea is that universes might be created as experiments. Our own world is full of laboratories, where scientists build smaller systems to test ideas. If a civilization could manipulate reality on the grandest scale, it might use universes themselves as tools of study. Each one could have different physical constants, different starting conditions, different rules of physics. Watching how they unfold would reveal knowledge that could never be gained otherwise. In this picture, universes would be like cosmic test tubes, each running its own version of reality. Some suggest that universe creation might not be entirely deliberate. If the laws of physics allow for it, then advanced civilizations experimenting with high-energy phenomena might create universes as a byproduct without fully intending to. Just as splitting the atom opened the door to nuclear reactions, tinkering with space-time itself could accidentally open a doorway to something bigger. In that case, universes would not be monuments, colonies, or experiments. They would be side effects. Of course, motives might be shaped by ethical or philosophical concerns as well. A civilization might create a universe not just because it can, but because it believes it should. If life is rare, or if intelligence is fragile, then making universes could be seen as a way of protecting the spark of existence. Imagine a species that sees itself as the caretaker of life in all forms. For them, universe creation might not be an act of pride or ambition, but of duty, a way of ensuring that life continues, no matter what happens to their own cosmos. In this sense, universes could be gardens, planted with care to carry forward the possibility of awareness. But motivations could also take darker forms. History shows us that power often tempts civilizations to test the limits of control. For some, the creation of a universe could be an act of dominance, a way of playing God. To shape reality would be the ultimate expression of authority. If such motives seem extreme, it is worth remembering that the scale of thought expands with the scale of power. What seems unimaginable to us might appear natural to beings who have already mastered the stars. To them, creating universes might not feel like arrogance, but like destiny. Survival, expansion, legacy, experimentation, accident, ethics, power, and creativity, each of these reflects something we already see in human behavior, only magnified to a cosmic scale. If intelligence develops in similar ways across realities, then the motives we understand may also apply beyond us. What we ask of ourselves, how do we survive, how do we matter, what do we create, might also be asked by civilizations with the ability to shape universes. If you created one, would you know? When humans build something, whether it's a house, a car, or even a planet-sized machine, we expect to interact with it. We can drive it, live in it, or at the very least point a telescope toward it. But a universe is not like a machine sitting in a laboratory. If one can be born from an artificial process, it might instantly expand beyond any possible boundary of control, slipping out of its maker's grasp the moment it comes into being. The creators could only stand outside of it, knowing it exists, but unable to enter or confirm what goes on inside. If, for example, an advanced civilization managed to collapse matter into the conditions of a new Big Bang, the event would take place inside a bubble of space-time, potentially fully sealed off from their own. From their perspective, they may see only a black hole form. Inside, an entirely new reality might be unfolding without its originators ever being able to confirm it. The only evidence they would have would be the act of creation itself, a calculation that says this should have worked, paired with the silent darkness of the event horizon. For human beings, knowledge usually requires direct observation. Instead, these creators would have to rely on indirect reasoning. They might point to the mathematics that predicted the outcome, or to physical signatures that suggest something unusual had happened in their own cosmos. For instance, if universe creation resembles black hole formation, then a civilization could at least record the sudden birth of that black hole and interpret it as the doorway to another cosmos. Unless the creators somehow encoded a message into those laws, a kind of cosmic signature, the inhabitants would also remain unaware. Even if someone inside suspected an artificial beginning, they would have no way of proving it. The boundary of their universe would act like a one-way mirror, keeping all information sealed inside. Some have speculated about what such a signature could look like. If advanced beings created a universe with intentional design, they might try to embed a clue. Perhaps they could leave behind a pattern that would only be noticed once a civilization became advanced enough to look. But any such message would have to be coded in a way that survived billions of years of cosmic evolution and that could be interpreted by entirely unknown forms of intelligence. The odds of such a message being noticed, let alone understood, are slim. Even without such a message, one could imagine civilizations convincing themselves that they know a universe was made, even if they cannot observe it directly. For example, if the mathematics behind their theory predicts with precision that creating certain conditions will result in a new universe and they carry out the steps exactly, they may accept that the outcome must be real. To them, the absence of direct evidence may not matter. Their confidence in the laws of physics might be enough. This is similar to how scientists on Earth believe in the interior of black holes, even though no one can see inside. The theory is trusted because it consistently explains everything else around it. Still, the psychological gap remains. To create something so immense, yet never be able to confirm it, would feel deeply unsatisfying. For beings capable of such feats, this question might shape their philosophy, their science, and even their sense of meaning. What if the very act of creating a universe subtly altered their own? Perhaps the process of pinching off a bubble of space-time would leave behind ripples or drain energy in a measurable way. If so, then the creators might not see the new universe, but they could notice changes in their own. Normally, building something implies a relationship between maker and creation, but here the creators would not guide or shape the outcome, nor would they watch it unfold. Instead, they would simply set the conditions and let the new universe write its own story. In that sense, perhaps the only real knowledge the creators could have would be the knowledge of potential. They could never confirm the details of what follows, but they would know that the spark had been struck, that something beyond them had been allowed to happen. The hunt for anomalies in the cosmic microwave background. When satellites like COBE, WMAP, and Planck mapped the CMB, the expectation was that the fluctuations would look like random noise, seeded by quantum variations in the earliest moments of inflation. And indeed, the overall pattern matches predictions of the standard cosmological model. But scattered through that pattern are unusual features that don't seem to fit perfectly. These are what scientists call anomalies. They are statistical oddities, places where the microwave background doesn't line up with the neat random structure we would expect if inflation had played out in isolation. One of the most talked about anomalies is the so-called cold spot. Found in data from the WMAP satellite and confirmed by Planck, this region of the sky is cooler than its surroundings by about 70 microkelvins, tiny in everyday terms, but significant when measured against the background of cosmic uniformity. The cold spot spans hundreds of millions of light-years, and ordinary explanations, like random chance or the presence of a large void in the distribution of galaxies, haven't fully settled the debate. Some have floated the idea that it could be the scar of another universe brushing against ours. The cold spot has become the poster child for this hypothesis, though it remains just one data point among many. Beyond the cold spot, there are other oddities. The large-scale alignment of temperature variations, sometimes called the axis of evil, shows an unexpected preference for certain orientations across the sky. Instead of random directions, the fluctuations on the largest scales seem to line up in a way that defies simple explanations. Some researchers suggest it could be a statistical fluke, while others wonder if it might hint at physics beyond the standard model, or even the fingerprints of structures from outside our cosmic bubble. There are also smaller-scale anomalies, hemispherical asymmetry, where one half of the sky appears slightly different from the other, and strange alignments between low-order multipoles, which are the patterns scientists use to break down the fluctuations mathematically. Each anomaly by itself may not be convincing. Together, they form a puzzle that cosmologists can't quite ignore. The CMB is the best window we have into the very early universe. If there are signs of new physics, or of neighboring universes, this is where we are most likely to see them. The challenge is separating what's real from what's noise. Our instruments are sensitive, but no observation is perfect. Systematic errors, foreground signals from our own galaxy, or statistical quirks can all create patterns that look like anomalies. That's why every candidate signal is studied, restudied, and debated for years. The cold spot, for example, has been subjected to many explanations. Some suggest it might be the result of a supervoid, an unusually large region of space with fewer galaxies than average, lying between us and that part of the CMB. Light passing through such a void would lose energy, creating the illusion of a colder patch. Surveys of galaxies in that region have indeed found hints of a large void, but whether it is enough to explain the cold spot completely remains uncertain. Others argue that the statistics of the fluctuations mean that an occasional cold patch is not surprising at all. In that view, the cold spot is nothing more than a chance event. But the possibility that it is more than chance is what keeps the discussion alive. If the cold spot is a relic of a cosmic collision, it would be one of the first observational hints of the multiverse. It would mean that our bubble is not alone, and that its history includes an encounter with another bubble that formed nearby in the inflationary sea. Such a discovery would shift the multiverse from a speculative idea into a testable framework. Even so, proving such a claim is extremely difficult. The CMB gives us only one sky to observe, one sample of the universe's history. Unlike laboratory experiments, we can't repeat the Big Bang to see if anomalies reappear. That's why anomalies are often controversial. They exist at the edge of what can be explained with confidence. Some cosmologists argue that chasing them risks over-interpreting random fluctuations. Others see them as the best hope for breakthroughs in understanding. The effort to detect anomalies is also pushing technology forward. The Planck satellite gave us the most detailed map so far, but future missions aim to go even deeper. Projects like CMB-S4 on the ground, or possible space-based successors, will measure polarization of the CMB with unprecedented precision. Polarization patterns could provide new evidence for collisions with other universes, as the interaction might leave a distinct signature in the way light is oriented. If one day a consistent, undeniable pattern emerges, something that cannot be explained by chance, voids, or instrumental error, it would force us to rethink our place in reality. The faint radio glow from billions of years ago would not only be the echo of our beginning, but also the record of encounters that shaped us in ways we are only beginning to guess. Gravitational waves as messengers from before time. Gravitational waves are unlike almost anything else we can observe in the cosmos. Where light can be absorbed, scattered, or bent, these ripples in the fabric of space-time glide through the universe almost without interference. They are not carried by particles in the same way photons carry light, but instead represent distortions in space-time that spread outward at the speed of light. Because of this, they can move through regions of space that would be opaque to any other form of signal. This makes them not just a new tool for astronomy, but possibly a unique one for answering questions about the very beginning of everything. If there is any messenger that could come to us from before time as we know it began, gravitational waves may be the closest we will ever get. For most of human history, the only way we studied the universe was by collecting light, first with our eyes, later with telescopes, and eventually across the entire electromagnetic spectrum. Yet all of these methods are trapped by the same limit. We cannot see past the CMB. Anything before that is hidden from us because light simply could not pass through the dense soup of particles. Gravitational waves, however, do not play by the same rules. They could, at least in theory, have passed through the early chaos unhindered. If we could detect them from those earliest instants, they would give us a direct line of sight into an era otherwise lost to history. The challenge is that gravitational waves from such ancient times would not look like the waves detected from merging black holes or colliding neutron stars, which are short bursts with specific patterns. Instead, they would be stretched and weakened by the vast expansion of the universe, becoming what physicists call a stochastic background. Rather than a single clear event, it would be more like a faint, ever-present hum woven into the fabric of space itself. Detecting such a background would be like trying to hear a soft, constant vibration beneath the noise of all other cosmic events. Yet if it could be done, it might reveal not only the conditions of the early universe, but also what, if anything, existed before the Big Bang. One of the most exciting possibilities involves inflation, which predicts that gravitational waves should have been produced during that period, ripples created by the stretching of space-time. These primordial gravitational waves would carry the signature of inflation, and finding them would be one of the most profound discoveries in physics. They would serve as direct evidence of how the universe was born. Attempts to find these waves have already taken place. Experiments like BICEP 2 at the South Pole looked for subtle twists, called B-modes, in the polarization of the CMB that might be left by primordial gravitational waves. For a moment in 2014, it seemed they had succeeded. Headlines around the world announced the first direct glimpse of gravitational echoes from the birth of the universe. But further study revealed that the signal could be explained by interstellar dust rather than ancient waves. The disappointment was sharp, yet it highlighted just how close we may be to uncovering something extraordinary. Beyond inflation, gravitational waves also open doors to other ideas. If our universe interacted with other universes, gravitational waves could leave faint scars, subtle distortions that stretch across all of space. Detecting such patterns would not just tell us about our own universe's beginnings, but could hint that others exist beyond our horizon. Gravitational waves could preserve echoes of an earlier cycle. If the universe is part of an eternal sequence, the ripples we might one day detect would be like whispers from an earlier cosmos, surviving across unimaginable stretches of time. Detecting these signals, however, demands instruments far beyond what we currently have. The waves from black hole mergers, discovered in 2015 by LIGO, were already faint, distorting space-time by less than the width of a proton. Primordial gravitational waves would be even more elusive, requiring detectors of incredible sensitivity. Projects such as LISA, a planned space-based observatory consisting of satellites linked across millions of kilometers, aim to open this window. Others look to pulsar timing arrays, where astronomers measure the precise rhythms of distant pulsars to detect subtle disruptions caused by passing waves. Both methods hold promise, but they are steps toward a goal that may take generations to achieve. Still, the allure of what might be found makes the effort irresistible. For billions of years, these ripples have been carrying information across the cosmic ocean, waiting for beings capable of listening. The fact that we have begun to hear them at all is a staggering achievement. What lies ahead is the possibility of tuning our ears even more finely, to catch the whispers from before time itself, from an era when the universe had not yet become what we know. They may be the only surviving traces of a pre-Big Bang reality. Searching for shadow universes in the dark matter mystery, the stars, galaxies, and planets we can see only make up a tiny fraction of the total mass and energy of the cosmos. The rest, most of it in fact, is invisible. Dark energy makes up the majority, but even before that puzzle, astronomers discovered dark matter. This is the unseen mass that holds galaxies together, keeping them from flying apart as they spin. Without it, the stars at the edges of galaxies should escape into space. Instead, they remain bound. Something invisible and powerful must be there. Yet after decades of searching, we still don't know what it is. The most common explanation is that dark matter is made of some kind of unknown particle, unlike the familiar ones we already know: protons, neutrons, and electrons. Many experiments have been built to detect such particles, from deep underground laboratories to particle accelerators. But time and again, they come up empty. This has led to more radical ideas. What if dark matter is not just a particle, but the shadow of another universe? The idea sounds dramatic, but it grows naturally from the mystery itself. Dark matter doesn't interact with light, which is why it is invisible, but it does interact with gravity, since we can measure its pull on galaxies. This strange mix, gravitational influence without light, is exactly what we might expect if our universe were brushing against another one, overlapping slightly in ways that only gravity can reveal. Perhaps there could be a parallel mirror cosmos with its own matter, forces, and possibly even life. This mirror matter wouldn't interact with ours through light or electromagnetism. Instead, it would drift through us, unnoticed, except for the fact that its gravity tugs on our stars and galaxies. To us, it would appear as the missing mass we call dark matter. To them, we might be the ghostly counterpart, equally invisible and puzzling. Some scientists imagine that dark matter might actually be ordinary matter, but ordinary in a different universe. If two universes are layered close together, their gravitational fields might overlap. This means galaxies in one universe could be affected by matter in the other. Our cosmos might be part of a grander structure, a kind of cosmic honeycomb, where multiple universes touch at their edges, leaking influence into one another. If true, then what we call dark matter could just be the neighboring universe leaving fingerprints on ours. This idea even has testable consequences. If dark matter comes from a shadow universe, then it might clump together differently than if it were made of particles alone. Galaxies could form in unusual shapes, or clusters of galaxies might move in ways that don't match predictions from standard models. Astronomers study large surveys of galaxy motions to search for these hints. For example, the strange distribution of dwarf galaxies around the Milky Way has puzzled scientists. Instead of being scattered randomly, they form a thin, disc-like structure. Could this be a clue that something beyond our universe is shaping them? Another line of research asks if dark matter could occasionally mix with normal matter. If universes overlap, perhaps once in a while, particles from one side cross over. Some experiments are now being designed to look for this. One example is the search for neutron oscillations, where a neutron in our universe might vanish and reappear in a mirror version. If such an effect were detected, it would be one of the most direct pieces of evidence for a shadow world. Cosmic observations also provide places to look. The early universe, in its hot and dense state, was a playground of interactions. If another universe influenced ours at that time, we might find the signs. Patterns of temperature and polarization could hold signatures of a hidden partner. Some researchers have studied certain anomalies, wondering if they point to contact with another domain. There is also the question of dark energy, the force driving the universe's expansion to speed up. If dark matter is linked to a shadow universe, perhaps dark energy is too. The push and pull between universes could create effects that mimic these mysterious forces. What we see as acceleration may in fact be the tug of a neighboring cosmos pulling space in strange directions. These are not mainstream explanations, but they are not dismissed outright either. The mystery of dark matter is so deep that all possibilities deserve exploration. The shadow universe hypothesis transforms the question from what particle are we missing to what realm are we blind to. If dark matter is another universe, then we are already in contact with it, whether we realize it or not. Every time a star orbits in a galaxy, part of its motion is dictated by matter that belongs to another world. This means that, at a very basic level, our existence is tied to a cosmos we cannot see. We are not isolated, not fully self-contained, but part of a bigger web. Instead of asking if there are aliens in distant galaxies of our universe, we could be asking if there are beings in the shadow one. If such a universe has stars, planets, and chemistry, then it might have evolved its own forms of life. To them, we would be invisible, just as they are to us. Yet we both influence each other through the silent medium of gravity. That possibility blurs the line between science and imagination, but it also widens the scope of what it means to search for neighbors in the cosmos. Could subtle patterns in dark energy reveal a parent universe's handprint? Most models of dark energy treat it as something uniform, the same everywhere, like an invisible pressure filling all of space. In this view, dark energy has a constant density that does not clump or vary from one place to another. It acts like a smooth background field, steadily driving expansion. But what if this assumption is not true? If dark energy has subtle variations across the cosmos, then those differences might carry meaning. They could hint at structures or influences that go beyond what our universe alone can explain. In other words, by looking carefully at the texture of dark energy, we might find signs of a parent universe, or evidence that our cosmos was born out of a larger reality. The challenge is that dark energy is extremely difficult to study. We cannot measure it in a laboratory or detect it with a sensor. We only infer its presence by watching how galaxies move apart over billions of years. This makes searching for subtle variations a task of extraordinary delicacy. Scientists use surveys of galaxies, maps of the CMB, and gravitational lensing data to look for any irregularities in how expansion behaves. If dark energy is not perfectly smooth, it might show up as tiny deviations in these observations. For example, one region of the universe might expand just slightly faster than another, or the CMB might show faint asymmetries not accounted for by standard models. Some theories suggest that dark energy could actually be a field, similar in nature to the Higgs field. If so, this field might have a complicated structure, and its behavior could vary depending on conditions inherited from before the Big Bang. Others take the speculation further and suggest that what we call dark energy might be an interface between universes. The boundary between our bubble and the outside might produce effects we experience as dark energy. If that is true, then variations in dark energy would be shaped by whatever lies beyond our cosmic horizon. Dark energy is already so elusive that even proving its uniformity or variation is a massive challenge. The data we have now is not precise enough to draw firm conclusions about subtle patterns. Moreover, many possible variations could also be explained by simpler physics within our universe alone. For instance, dark energy might be connected to the quantum vacuum, and its apparent irregularities could arise from quantum processes rather than outside influences. To move forward, scientists will need vastly more detailed measurements, collected over decades by future telescopes and detectors. Projects like the European Space Agency's Euclid mission and NASA's Roman Space Telescope are designed to map the cosmos in extraordinary detail, tracking billions of galaxies across cosmic history. These missions aim to clarify how dark energy evolves and whether it is truly constant. If they discover even small deviations from uniformity, the implications could be immense. It would not prove the existence of a parent universe, but it would open the door to exotic explanations. Wormholes and the dream of inter-universal travel. Wormholes are tunnels, shortcuts through the fabric of space and time, bending the rules that normally keep distant regions of the cosmos apart. While most discussions about wormholes focus on using them to cross great distances within our own universe, another line of thought dares to go further. What if wormholes could link not just stars and galaxies, but entirely separate universes? A wormhole, in its simplest description, is a solution to Einstein's equations of general relativity. If space can bend, then in theory it can also fold and connect 2 points together. Mathematically, wormholes are possible, though whether nature allows them to exist is another matter. The versions most people know come from popular culture, where they act as portals between distant planets. But within the equations, wormholes are not limited to our universe alone. If there are other universes, as many theories suggest, then wormholes might provide a bridge across what otherwise seems like an unbridgeable divide. To understand this idea, it helps to think of the universe not as a flat sheet, but as a higher dimensional structure. If our universe is like a bubble floating in a larger space, then a wormhole could be imagined as a tunnel piercing one bubble's surface and opening into another. The tunnel would not exist within our space, but rather as a higher dimensional passage, outside what we normally perceive. The mathematics allows such constructs, though the stability of these structures is a constant problem. For a wormhole to remain open, it would require something known as exotic matter. This is matter with negative energy density, something not found in ordinary physics. Without it, the immense gravity of the wormhole would crush it closed faster than anything could pass through. Exotic matter has not been observed, but quantum physics suggests it might not be entirely impossible. Certain quantum effects, like the Casimir effect, already create situations where energy seems to behave strangely, hinting at loopholes in the rules. But even if exotic matter exists, the amount required to hold open a wormhole large enough for travel would be vast, far beyond what any civilization could likely gather. If advanced civilizations could harness exotic matter, perhaps they could build wormholes on a cosmic scale. And if they could do so, why stop at linking stars? Why not aim higher and connect entire universes? For beings capable of manipulating space-time so profoundly, the difference between interstellar and interuniversal travel might be less daunting than it appears to us. It would simply be like climbing out of one room and into another. Of course, the difficulties extend far beyond engineering. There is the question of where such a wormhole would open. Within our universe, the other end could in principle be placed anywhere. But if the wormhole reaches beyond our cosmos, it is unclear how one would select a destination. The other side might open into a universe with entirely different physical laws. Perhaps there would be no stable atoms, no light, no recognizable matter at all. Entering such a universe could mean instant destruction, as everything we are made of would dissolve or fail to function. Even communication across such a divide would be almost impossible, since signals we use, whether light, radio waves, or particles, might not even exist there. Perhaps black holes could act as natural wormholes. According to certain solutions in general relativity, the interior of a black hole may connect to another region of space-time, perhaps even another universe entirely. This idea is often described with the term Einstein-Rosen bridge, an early form of the wormhole concept. If true, then every black hole could be a gateway. Yet the catch is that such bridges are unstable. Anything attempting to cross them would be crushed by the singularity before reaching the other side. Quantum mechanics might soften this, but so far, no evidence suggests black holes are functioning portals. Even so, it is fascinating to imagine what it would mean if a wormhole to another universe could be opened. Suddenly, the idea of being trapped within our cosmic bubble would vanish. Civilizations might discover entirely new realms, perhaps endless in number, each with its own rules of physics. The dream of exploration would expand far beyond galaxies into a multiverse where every possible variation of existence might be found. To some, this is the ultimate form of discovery, where the boundary of knowledge is not a single universe, but an infinite landscape. Yet most physicists remain cautious. The mathematics allows wormholes, but the physical requirements seem too extreme. The universe appears to enforce rules that prevent such passages from being usable. For instance, quantum effects may cause wormholes to collapse as soon as anything tries to pass through, creating a kind of natural censorship. This would mean that while wormholes exist in the math, reality itself forbids them from being more than fleeting structures. It is as if nature dangles the idea before us, only to close the door before we can step through. Wormholes represent the ultimate form of travel, whether they are forever locked away in theory or one day become tools for civilizations far beyond our own remains unknown. But the fact that physics seems to support them keeps the hope alive. Are universes fundamentally separate or deeply entangled? When two particles are entangled, their states are linked in such a way that what happens to one instantly affects the other, even if they are far apart. It doesn't matter if they are separated by inches or by light years. The connection seems to transcend distance. Now, imagine extending this concept beyond our universe. If universes can emerge from the same process, could they carry with them hidden threads of entanglement, weaving together realities we usually think of as disconnected? Some theories propose that universes may emerge in clusters. If two universes form together from the same quantum field, it's possible that they could retain a form of entanglement with one another. In that case, what happens in one universe might, in some subtle way, be reflected in the other. The connection would not be obvious. It wouldn't be like seeing galaxies appear out of thin air, but it could show up as slight statistical correlations, patterns that hint at an unseen hand-linking worlds. If universes could be entangled, it would change how we think about causality and independence. We are used to the idea that our universe is self-contained. Its particles, forces, and fields all interact within its boundaries, and nothing from the outside plays a role. But if entanglement extends across universes, the story becomes more complicated. It means that what looks like randomness in our universe might not be purely random at all, but influenced by hidden variables tied to another universe. Some have speculated that this could provide a way to explain the origin of certain physical constants. If universes are entangled, they might not each have independent parameters. Instead, they could share information, balancing each other out. In quantum mechanics, measuring a particle in one place instantly collapses its entangled partner into a corresponding state. Could the same thing happen on a cosmic scale? If an intelligent observer in one universe measured a certain property of reality, could that action affect the state of another entangled universe? Some suggest that if universes are entangled, they may not be entirely stable on their own. Instead, their existence could depend on being part of a larger web of connected realities. If one universe were somehow to collapse or fade away, the others could be affected, like a network of dominoes where a single fall changes the balance of the whole. This would make the multiverse less like a library of disconnected books and more like an ecosystem, where the health of one part influences the survival of the rest. If minds themselves are products of quantum processes in the brain, and if those processes are entangled at the deepest level of reality, then consciousness might not be entirely confined to one universe. This suggests that what we think of as individuality and isolation might be illusions, and that existence is threaded together in ways far beyond our current perception. Skeptics, of course, point out that while the mathematics of entanglement works beautifully for particles, scaling it up to universes is an enormous leap. It's one thing to entangle photons in a laboratory, It's another to claim that entire universes could share a quantum link. What does it mean for universes to be entangled? What are the observables, the measurable quantities that would confirm it? Without clear answers, the notion remains a poetic extension of physics rather than a hard scientific proposal. Is fine-tuning an illusion? The physical constants that shape the universe seem perfectly balanced. If they were even slightly different, stars might not shine, atoms might not hold together, and life would never have appeared. From this view, the universe looks like it was delicately set up, as though someone adjusted a set of cosmic dials with great care. But not everyone accepts this picture at face value. A growing number of scientists argue that what we call fine-tuning may not be as special or as mysterious as it first appears. One of the main reasons fine-tuning is questioned comes from the history of science itself. Again and again, humans have believed that certain things were special or finely arranged, only to later discover natural explanations. For centuries, Earth seemed like the unique center of the cosmos, placed perfectly to host life. Later discoveries showed that Earth is simply one planet orbiting an ordinary star in an ordinary galaxy. What once looked like a cosmic privilege turned out to be a natural outcome of physical processes. Some physicists suggest that fine-tuning might follow the same path. Instead of being the result of chance or an infinite multiverse, the values of the universe might flow naturally from deeper physical laws we don't yet know. In this view, the just right numbers could be inevitable, not accidental. The illusion of fine-tuning often arises from the way we frame the problem. Take the example of gravity. Its strength seems delicately balanced, allowing stars to form but not collapse too quickly. But the way physicists measure the strength of gravity depends on the system of units and constants chosen. If you describe gravity using different mathematical frameworks, the apparent need for delicate adjustments can vanish. What seemed like an improbable value becomes just a natural feature of the equations. Some argue that fine-tuning is partly a human-made artifact, shaped by the way we define constants and compare them. In other words, the universe might not be as special as it looks once we take a step back and view it through a different mathematical lens. Another angle comes from the search for unification in physics. General relativity and the standard model of particle physics work brilliantly in their own domains, but don't fit together easily. Many physicists believe that one day they'll be unified into a single deeper theory, something often referred to as a theory of everything. If such a theory exists, the values we call fine-tuned today may simply fall out of its equations. Just as the boiling point of water is not arbitrary but the result of molecular physics, the strength of forces or the mass of particles might be determined by unavoidable rules. If that's true, then fine-tuning is an illusion created by our incomplete knowledge. There's also the anthropic perspective, which says we only notice fine-tuning because we're here to observe it. But critics argue that this is a misleading way to think. For example, when we look at Earth's distance from the Sun, we see that it sits in the habitable zone, where liquid water can exist. It feels special. Yet when scientists study planetary formation, they find that habitable zones occur naturally around many stars, and given enough planets, it's not surprising that at least one would land in the right spot. By analogy, some suggest that the values of physics might not be as rare as we think. Perhaps the laws of nature strongly favor universes that allow complexity and structure. If so, then life-friendly conditions are not a cosmic lottery ticket, but a natural outcome of the rules themselves. In the quantum world, probabilities dominate. Events that look highly improbable on human scales happen constantly at microscopic ones. This raises the possibility that our view of what is unlikely is skewed by intuition. What looks improbable to us might, in fact, be the most probable outcome once we fully understand the quantum foundations of the universe. It could be that fine-tuning is less about cosmic luck and more about how the strange logic of quantum mechanics scales up to the world we see. When scientists talk about fine-tuning, they usually focus on a handful of constants, like the speed of light or the strength of the nuclear force. But what if those aren't truly independent? What if they are linked by deeper relationships? Imagine trying to explain why a car engine works without realizing that pistons and fuel injectors are connected. You might treat each part as though it had to be tuned separately, when in fact they are parts of a larger whole. Similarly, the constants of nature may not be separate dials that can be adjusted freely. They may be bound together, which would make the appearance of fine-tuning vanish. Even within known physics, there are hints that values can emerge naturally from symmetry. Symmetry plays a powerful role in shaping the laws of the universe. The fact that electric charges balance so perfectly, for example, is not a cosmic accident, but a result of deep symmetry in quantum field theory. Many physicists suspect that other constants we call fine-tuned might also be explained by hidden symmetries. As we uncover more of these, the mystery of fine-tuning could shrink further. Still, some thinkers warn that dismissing fine-tuning as an illusion might go too far. Even if deeper laws set the constants, there's still the question of why those laws exist in the first place. If a theory of everything someday shows that the universe could only ever take the form we see, that might solve one puzzle while raising another. Why does that theory exist at all? For critics of the fine-tuning problem, this might be an unavoidable horizon. Every explanation shifts the question to a deeper layer, and the illusion of fine-tuning could simply be hiding an even more fundamental mystery. The debate over fine-tuning and its alternatives shapes how we view the universe. If fine-tuning is real, it suggests either staggering cosmic luck or the existence of countless unseen universes. If it's an illusion, then the universe may be more self-contained, governed by natural laws that leave no room for chance. Telescopes, colliders, and simulations of creation. The Big Bang sits like a curtain on the far edge of time, blocking us from seeing further back. Yet, even if we can't pierce it directly, our tools keep improving, giving us glimpses that edge ever closer to those first moments. Each new telescope, detector, and computer simulation adds another piece. Together, they form a kind of proxy vision, allowing us to test theories about what lies beyond the observable universe, and perhaps even about whether multiple universes exist. Modern telescopes are at the forefront of this hunt. The James Webb Space Telescope, for instance, has already shown us galaxies that seem to form too early, too bright, and too massive compared to what our models predict. Some scientists wonder if these unexpected structures hint at flaws in our understanding of the universe's beginning. If galaxies appear sooner than they should, could that point toward physics we don't yet know, or even conditions shaped by something outside our universe? Future telescopes, even more advanced than Webb, will push this search further. Projects like the extremely large telescope in Chile, with a mirror nearly 40 meters wide, will collect enough light to study the faintest and oldest stars. By examining how matter grouped together in the first billion years after the Big Bang, astronomers hope to indirectly test ideas about inflation and other theories of cosmic birth. LIGO and Virgo have already revealed the hidden collisions of black holes and neutron stars. Now new generations of gravitational wave detectors, like LISA, promise to go deeper. If certain patterns are found in the background of these waves, they could point to processes that happened before the Big Bang or during inflation. For example, cosmic strings, hypothetical defects in space-time left over from the universe's earliest moments, could leave behind gravitational wave signals. Detecting them would be like hearing an echo from the birth of reality. But telescopes and detectors can only go so far. To complement them, physicists turn to colliders. Particle accelerators like the Large Hadron Collider allow us to recreate, in miniature, the extreme conditions that existed in the universe's first fractions of a second. When protons smash together at near light speeds, the collisions produce bursts of energy that briefly mimic those ancient temperatures and densities. Through these experiments, researchers study how fundamental particles behave and interact. Discoveries such as the Higgs boson have already reshaped our picture of reality. Looking ahead, larger colliders are being proposed, ones that could push to even higher energies. The hope is that they might uncover evidence of new particles that could explain mysteries like dark matter, or show whether extra dimensions of space might exist. Another frontier lies in the digital realm. Supercomputers now allow scientists to simulate universes from scratch, starting with the basic ingredients of physics and letting them evolve across billions of virtual years. These simulations are critical tools for testing our theories. If a simulation that uses known physics can reproduce the universe we observe, then we know our models are on the right track. But if the simulated universes consistently fail to match reality, it suggests something important is missing. Some simulations test different values for the fundamental constants of nature. By running billions of variations, researchers explore what kinds of universes could exist and which ones could support life. In doing so, they indirectly explore the multiverse hypothesis, showing just how unusual, or perhaps inevitable, our own universe might be. One of the most ambitious goals is to simulate the very first instance after the Big Bang. This is incredibly difficult because the energies and densities involved are so extreme. Yet researchers are pushing forward, building models that include quantum effects, inflationary expansion, and exotic particles. These simulations allow scientists to see what signatures would remain billions of years later if certain processes occurred. Armed with these predictions, astronomers know what to look for in real data. All these different approaches support one another. Telescopes provide direct observations. Colliders test the fundamental rules, and simulations tie the two together into coherent pictures. Each advance pushes the boundary of what is possible. We may never see the Big Bang itself, but by combining these tools, we can map out its edges and begin to understand the unseen. Already, we stand at a remarkable crossroads. Our instruments are reaching levels of sensitivity that earlier generations of scientists could hardly dream of. Yet with each answer, new questions arise. What happens if telescopes continue to find galaxies that shouldn't exist under our current theories? What if gravitational waves reveal structures that can't be explained by known physics? What if colliders find no new particles at all, leaving the mystery of dark matter unsolved? These possibilities remind us that technology does not guarantee absolute clarity. It often opens new mysteries. Still, the pursuit is worth it. To search for the origin of everything, even indirectly, is to confront the deepest questions we can ask. The experimental horizon. How far can science really reach? There is a line in science that is often invisible until we stumble upon it. It is the line that separates what we can test from what we can only imagine. The multiverse sits close to that line, sometimes crossing it, sometimes hovering near enough that we wonder if one day we might drag it back into the realm of testable science. The question is whether that will ever be possible, or whether the multiverse will always remain just beyond the reach of our instruments, an idea that can be described in mathematics, but never touched in reality. The story of physics has often been about pushing the experimental horizon outward. In Galileo's time, the horizon was the sky itself, revealed by a telescope only a few centimeters wide. Centuries later, particle accelerators extended it inward, peeling back the layers of matter to reveal quarks and gluons. Space probes have done the same on the cosmic scale, turning what was once invisible into something measurable. Each generation of technology makes the impossible possible, and yet there are always limits that seem unbreakable. The speed of light, the edge of the observable universe, the quantum fuzziness that blurs certainty, all of these mark the outlines of a horizon we cannot easily cross. When we talk about proving or disproving the multiverse, we run headlong into these limits. Other universes are beyond our observable cosmos. They would lie outside the bubble of space-time from which light has had time to reach us. We cannot send a probe across the cosmic horizon to take a snapshot. We cannot wait for light that will never arrive. Karl Popper, the philosopher of science, argued that a scientific idea must be falsifiable, that is, it must be possible in principle to prove it wrong. If no observation could ever disprove the multiverse, then is it really science? Critics say no, that without falsifiability, the multiverse drifts into metaphysics. Supporters counter that strict falsifiability has always been a fuzzy rule, and that in practice, science often works by degrees of plausibility rather than absolute tests. After all, we cannot see quarks directly either, but we accept them because of their explanatory power. History shows that frontiers we once thought unreachable can be crossed. Gravitational waves were predicted 100 years before they were detected. Black holes were once mathematical curiosities, now photographed in glowing halos of gas. Dark energy was invisible until clever experiments revealed its imprint on distant galaxies. Perhaps the multiverse too will one day slip across the horizon. But there is also a sobering possibility that some questions are permanently beyond us. The horizon may not always retreat. There may be mysteries baked into the structure of reality that no experiment can ever touch. If that is true, then physics will not end. It will adapt. It will still build models, still search for coherence, still push against the edges. But it may have to live with the idea that not every question has an answer we can prove. The multiverse may remain one of those questions, tantalizing, endlessly discussed, but always just out of reach. How would you rate humanity's chances of pushing past the horizon? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.